If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The Silent Architect. What is dark matter? The cosmos holds secrets so profound that even with our most advanced instruments, they remain hidden in plain sight. One of the greatest mysteries lurking in the shadows of our understanding is dark matter. It is the silent architect of the universe, shaping the galaxies we see, governing the motion of celestial bodies, and yet eluding direct detection. But what exactly is dark matter, and why has it captivated the minds of scientists and stargazers alike for decades? Imagine staring at a night sky glittering with stars, knowing that everything visible, every planet, star, gas cloud, and nebula, accounts for less than 5% of the universe's total mass and energy. This realization is not merely humbling, it's transformative. It challenges our perceptions of reality and beckons us toward deeper exploration. Beyond the dazzling spectacle of visible light lies an enormous, unseen world. Dark matter, an enigmatic substance that neither emits nor absorbs light, fills this hidden realm, quietly sculpting the cosmos into its current form. The concept of dark matter emerged not from imagination, but from necessity. In the 1930s, Swiss astrophysicist Fritz Zwicky observed something peculiar about galaxy clusters. These vast assemblies of galaxies moved in ways that defied expectations based on the visible matter they contained. Zwicky coined the term Dunkelmaterie, or dark matter, to describe this invisible mass that appeared to be holding galaxies together. At first, this idea seemed speculative, even improbable, but decades of evidence have since confirmed that the universe indeed harbors a mysterious, unseen presence. What makes dark matter so compelling is its interaction, or lack thereof, with ordinary matter. Unlike the particles we encounter daily, dark matter doesn't interact with electromagnetic forces. This means it neither shines nor reflects light, making it invisible to telescopes. Its presence is instead inferred from its gravitational effects on the cosmos. Galaxies spin faster than they should based on their visible mass alone, and the universe's large-scale structure, the web of galaxies and voids stretching across billions of light-years, cannot be explained without this shadowy substance. But if dark matter doesn't emit light or interact with it, what is it? Scientists propose that it might consist of exotic particles unlike anything in the standard model of particle physics. These particles, such as weakly interacting massive particles, WIMPs, or axions, could permeate the universe, influencing its evolution while remaining frustratingly undetectable by conventional means. Despite the lack of direct evidence, researchers continue their tireless quest to understand its nature. Dark matter isn't just an abstract concept confined to academic discussions. It's a phenomenon that underpins the universe's very fabric. Without it, galaxies wouldn't hold together, stars wouldn't form as they do, and the cosmos as we know it would unravel. Its fingerprints are everywhere, from the intricate dance of galaxy clusters to the ripples in the cosmic microwave background, the faint afterglow of the Big Bang. As our understanding deepens, new questions emerge. Could dark matter hold the key to undiscovered laws of physics? Might it harbor entire realms of existence beyond our perception? These questions aren't merely theoretical. They challenge us to rethink the boundaries of what we know and inspire us to seek answers in the unknown. In the chapters to come, we'll embark on a journey to explore the evidence for dark matter, the groundbreaking theories that seek to explain it, and the cutting-edge experiments striving to uncover its secrets. We'll delve into its role in shaping the universe, the cosmic puzzles it helps solve, and the challenges it presents to modern science. The universe is vast, and its mysteries are profound. Dark matter is the silent architect of this grand design, urging us to look beyond the visible and embrace the unseen. As we begin this exploration, let us ask ourselves, how much of reality lies hidden in the shadows, waiting to be unveiled? The Silent Architect. What is dark matter? The cosmos holds secrets so profound that even with our most advanced instruments, they remain hidden in plain sight. One of the greatest mysteries lurking in the shadows of our understanding is dark matter. It is the silent architect of the universe, shaping the galaxies we see, governing the motion of celestial bodies, and yet eluding direct detection. But what exactly is dark matter, and why has it captivated the minds of scientists and stargazers alike for decades? Imagine staring at a night sky glittering with stars, knowing that everything visible, every planet, star, gas cloud, and nebula, accounts for less than 5% of the universe's total mass and energy. This realization is not merely humbling, it's transformative. It challenges our perceptions of reality and beckons us toward deeper exploration. Beyond the dazzling spectacle of visible light lies an enormous, unseen world. Dark matter, an enigmatic substance that neither emits nor absorbs light, fills this hidden realm, quietly sculpting the cosmos into its current form. The concept of dark matter emerged not from imagination, but from necessity. In the 1930s, Swiss astrophysicist Fritz Zwicky observed something peculiar about galaxy clusters. These vast assemblies of galaxies moved in ways that defied expectations based on the visible matter they contained. Zwicky coined the term Dunkelmaterie, or dark matter, to describe this invisible mass that appeared to be holding galaxies together. At first, this idea seemed speculative, even improbable, but decades of evidence have since confirmed that the universe indeed harbors a mysterious, unseen presence. What makes dark matter so compelling is its interaction, or lack thereof, with ordinary matter. Unlike the particles we encounter daily, dark matter doesn't interact with electromagnetic forces. This means it neither shines nor reflects light, making it invisible to telescopes. Its presence is instead inferred from its gravitational effects on the cosmos. Galaxies spin faster than they should based on their visible mass alone, and the universe's large-scale structure, the web of galaxies and voids stretching across billions of light-years, cannot be explained without this shadowy substance. But if dark matter doesn't emit light or interact with it, what is it? Scientists propose that it might consist of exotic particles unlike anything in the standard model of particle physics. These particles, such as weakly interacting massive particles, WIMPs, or axions, could permeate the universe, influencing its evolution while remaining frustratingly undetectable by conventional means. Despite the lack of direct evidence, researchers continue their tireless quest to understand its nature. Dark matter isn't just an abstract concept confined to academic discussions. It's a phenomenon that underpins the universe's very fabric. Without it, galaxies wouldn't hold together, stars wouldn't form as they do, and the cosmos as we know it would unravel. Its fingerprints are everywhere, from the intricate dance of galaxy clusters to the ripples in the cosmic microwave background, the faint afterglow of the Big Bang. As our understanding deepens, new questions emerge. Could dark matter hold the key to undiscovered laws of physics? Might it harbor entire realms of existence beyond our perception? These questions aren't merely theoretical. They challenge us to rethink the boundaries of what we know and inspire us to seek answers in the unknown. In the chapters to come, we'll embark on a journey to explore the evidence for dark matter, the groundbreaking theories that seek to explain it, and the cutting-edge experiments striving to uncover its secrets. We'll delve into its role in shaping the universe, the cosmic puzzles it helps solve, and the challenges it presents to modern science. The universe is vast, and its mysteries are profound. Dark matter is the silent architect of this grand design, urging us to look beyond the visible and embrace the unseen. As we begin this exploration, let us ask ourselves, how much of reality lies hidden in the shadows, waiting to be unveiled? The missing mass. Why ordinary matter isn't enough. The universe is a masterpiece of vast proportions, its structure shaped by forces both seen and unseen. As we explore the cosmos, it becomes clear that ordinary matter, everything composed of protons, neutrons, and electrons, tells only part of the story. If stars, planets, and galaxies form the visible narrative, then dark matter is the invisible ink connecting the dots. But why isn't ordinary matter enough to explain the universe's grand design? And what does this reveal about the missing mass? Ordinary matter, known scientifically as baryonic matter, includes everything familiar to us, the atoms that compose water, air, rock, and life. It also includes the glowing gases in nebulae, the fiery plasma of stars, and even the superdense material of neutron stars. For much of human history, it was assumed that this matter accounted for everything in the cosmos. However, as we developed more sophisticated ways to observe the universe, glaring inconsistencies began to surface. One of the most significant discrepancies arises when measuring the gravitational effects observed in galaxies and galaxy clusters. For instance, galaxies rotate at speeds far greater than what visible matter can account for. Without an additional source of mass to generate the necessary gravitational pull, these galaxies should fly apart, their outer stars escaping into the void. Yet, they remain intact, as if bound by an unseen force. This mismatch between what we observe and what we calculate has persisted for decades, compelling scientists to seek answers beyond ordinary matter. On even larger scales, the distribution of galaxies throughout the universe forms a vast cosmic web. This intricate structure consists of clusters, filaments, and voids spanning billions of light years. The gravity of ordinary matter alone could not have sculpted this web in the time since the Big Bang. Dark matter, with its additional gravitational influence, provides the scaffolding on which ordinary matter accumulates to form galaxies and clusters. Without it, the universe's large-scale structure would be vastly different, less organized, less cohesive, and fundamentally less dynamic. Another compelling clue lies in the relic radiation of the cosmic microwave background (CMB). This faint glow, a remnant of the universe's fiery birth, is imprinted with patterns that reflect the density fluctuations of the early cosmos. These fluctuations acted as seeds for the eventual formation of galaxies and clusters. However, the observed distribution of these seeds cannot be explained by ordinary matter alone. Baryonic matter interacts with radiation, creating pressure that smooths out density variations. For the observed patterns to exist, an additional, non-interacting form of matter, dark matter, must have been present to amplify the gravitational clumping required for structure formation. The gravitational lensing of light further reinforces the necessity of dark matter. Observations of massive galaxy clusters reveal gravitational effects far exceeding what visible matter can produce. In these clusters, light from background galaxies is bent and magnified by the cluster's gravitational field. By measuring the degree of lensing, scientists can map the total mass distribution within the cluster. Time and again, these maps show that visible matter makes up only a fraction of the required mass. Dark matter fills the gap, exerting its influence silently but unmistakably. If ordinary matter falls so short in explaining the universe's behavior, why not consider other alternatives? Over the years, some have proposed modified theories of gravity, such as MOND, modified Newtonian dynamics, which suggest that the laws of gravity themselves may need revision on cosmic scales. While intriguing, these theories struggle to account for all the observed phenomena. For instance, they cannot explain the separation of dark matter and ordinary matter seen in galaxy cluster collisions like the Bullet cluster. In these cases, gravitational lensing clearly shows dark matter continuing its journey undisturbed, while ordinary matter, in the form of hot gas, slows and interacts. Such observations strongly support the existence of a distinct, non-baryonic form of matter. Ordinary matter is also insufficient when considering the total mass-energy content of the universe. According to measurements from missions like WMAP and Planck, baryonic matter constitutes only about 5% of the universe. Dark matter, on the other hand, accounts for approximately 27%, with the remaining 68% attributed to dark energy, a separate and equally mysterious force driving the universe's accelerated expansion. This distribution underscores how much of the cosmos lies beyond the realm of ordinary matter. The limitations of baryonic matter extend to its inability to explain the dynamics of individual galaxies and galaxy clusters. For example, dwarf galaxies, some of the smallest and least luminous galaxies, often exhibit disproportionately high rotational velocities. These velocities suggest the presence of substantial amounts of dark matter, as their visible mass alone cannot account for the observed motion. Similarly, in large galaxy clusters, the hot gas detected through X-ray emissions outweighs the combined mass of the stars within the cluster. Yet, Even this gas represents only a fraction of the cluster's total mass, with dark matter once again stepping in to fill the void. The idea that ordinary matter is insufficient challenges our perceptions of the universe. For centuries, humanity has relied on the tangible and the visible to define existence. Dark matter forces us to reconsider this bias, expanding our view to include the invisible forces that shape reality. Its gravitational influence is undeniable, yet its nature remains elusive, driving scientists to explore uncharted territories of physics. What could dark matter be? Is it composed of particles as yet undiscovered? Or does it represent something even stranger, like primordial black holes or exotic fields? The answers may redefine the boundaries of science, offering new insights into the universe's origin and evolution. As we continue to investigate, one fact becomes clear. The story of the cosmos cannot be told with ordinary matter alone. Dark matter is the missing mass, the hidden protagonist in the grand narrative of existence. It challenges us to look beyond the visible, to question the limits of our understanding, and to embrace the unknown. Ghost particles, theories on the nature of dark matter. What is dark matter? This question has baffled scientists since its existence was first inferred. Though invisible and elusive, dark matter is far from featureless. It has inspired countless theories and experiments aimed at revealing its true nature. Could dark matter consist of ghostly particles slipping through the fabric of the universe? Or might it embody something even stranger, something entirely beyond our current understanding of physics? To uncover the essence of dark matter, researchers have delved into the subatomic world, where particles interact in ways both familiar and exotic. One of the most compelling theories posits that dark matter is composed of weakly interacting massive particles, or WIMPs. These hypothetical particles interact with gravity like ordinary matter, but are otherwise imperceptible because they do not interact with electromagnetic forces. If WIMPs exist, they would have been created in the early moments after the Big Bang, forming a cosmic reservoir that persists to this day. WIMPs gain popularity because they naturally fit into extensions of the standard model of particle physics, particularly supersymmetry. This theoretical framework predicts the existence of a suite of particles that could include dark matter candidates. The advantage of WIMPs lies in their ability to explain many of dark matter's observed effects: their gravitational presence, their lack of electromagnetic interaction, and their abundance. However, despite decades of searching, direct evidence of WIMPs remains elusive. Another intriguing candidate is the axion, a lightweight particle predicted to solve a separate problem in quantum physics known as the strong CP violation problem. Axions, if they exist, would be extraordinarily abundant and could collectively account for the missing mass of the universe. Unlike WIMPs, which are relatively heavy, axions are incredibly light and interact even more weakly with other particles, making them particularly challenging to detect. Current experiments are probing the possible interaction of axions with electromagnetic fields, searching for faint signals that might reveal their presence. Sterile neutrinos present yet another possibility. Ordinary neutrinos, which are among the lightest and most elusive particles in the universe, are already known to exist in 3 varieties, or flavors. Sterile neutrinos would represent a 4th type, interacting only through gravity and the weak nuclear force. Their behavior could help explain certain anomalies observed in astrophysics, such as the motions of dwarf galaxies. If sterile neutrinos are the constituents of dark matter, their detection would require even more innovative methods than those employed for WIMPs or axions. While particle candidates dominate the discussion, alternative theories push the boundaries of conventional thinking. One such idea is that dark matter could be composed of primordial black holes, tiny black holes formed during the universe's earliest moments. These objects, though exotic, would exert gravitational influences consistent with dark matter's observed effects. Recent studies have sought to determine whether these black holes could account for dark matter's abundance, but the evidence remains inconclusive. Beyond individual particles or objects, some theories suggest that dark matter could emerge from entirely new physics. One provocative idea is the existence of dark sectors, hidden dimensions, or universes that interact with ours only through gravity. In such a scenario, Dark matter might consist of complex systems, akin to stars and planets, existing in a parallel cosmic framework. These dark sectors could revolutionize our understanding of reality, offering a glimpse into realms as yet unexplored. Another speculative avenue involves self-interacting dark matter. Unlike WIMPs, which interact minimally with themselves or other particles, self-interacting dark matter would possess the ability to collide and scatter within its population. This behavior could explain certain galactic phenomena that standard dark matter models struggle with, such as the distribution of dark matter in dwarf galaxies and galaxy clusters. Experiments around the world are racing to test these theories. Deep underground, in laboratories shielded from cosmic rays and other background noise, detectors search for fleeting interactions between dark matter particles and ordinary atoms. One approach involves cryogenic detectors, which aim to measure tiny temperature changes caused by a dark matter particle colliding with a nucleus. Another involves noble gas detectors, which look for scintillation or ionization signals produced by these rare collisions. Meanwhile, particle accelerators like the Large Hadron Collider are probing high-energy collisions that might produce dark matter particles directly. Though these experiments have yet to yield definitive results, they provide critical constraints on the properties that dark matter particles might possess. Astrophysical observatories also play a crucial role in the hunt for dark matter. Telescopes scan the skies for indirect evidence, such as gamma rays, X-rays, or neutrinos produced when dark matter particles annihilate or decay. One tantalizing signal comes from the center of our galaxy, where an excess of gamma rays has sparked debate over whether it could be a signature of dark matter. Similarly, observations of galaxy clusters have hinted at unusual emissions that some attribute to sterile neutrinos or axions. Despite the immense progress in testing these theories, dark matter remains stubbornly out of reach. Each null result narrows the possibilities, sharpening the focus of future research. Yet, with every experiment, the mystery deepens, raising questions that challenge the very foundations of physics. Could dark matter be more than one thing, a mixture of particles or phenomena? Could it represent an entirely new category of existence, transcending our current frameworks? The answers are likely to transform not only cosmology, but also our understanding of matter, energy, and the universe itself. As the quest to uncover dark matter continues, the stakes grow higher. The discovery of its true nature would mark a turning point in science, revealing a hidden side of the cosmos that has shaped its evolution since the dawn of time. For now, dark matter remains a ghostly presence, an enigma that beckons us to explore further, to push the boundaries of what we know, and to imagine the unimaginable. A dance of shadows, the role of dark matter in galaxies. The universe is a grand cosmic ballet, with galaxies pirouetting through space in intricate patterns. At the heart of this performance lies an invisible force guiding their motion and holding their forms together, dark matter. Without this enigmatic substance, galaxies as we know them would not exist. But what role does dark matter play in shaping these celestial structures? And why is it so crucial to their survival? Galaxies are vast systems of stars, gas, dust, and dark matter bound together by gravity. They come in various shapes and sizes, from majestic spirals like the Milky Way to spherical ellipticals and irregularly shaped clusters. At first glance, it seems that the visible matter, stars and glowing nebulae, dictates the dynamics of these systems. However, when scientists began measuring the motion of stars within galaxies, they uncovered a profound mystery. In the 1970s, Vera Rubin and her colleagues studied the rotation curves of spiral galaxies. Their observations revealed something unexpected. The outer stars of these galaxies were orbiting at much higher velocities than predicted by the gravitational pull of the visible mass alone. According to Newtonian physics, the rotational speed should decrease with distance from the galactic center, similar to how the outer planets in our solar system orbit the sun more slowly than the inner ones. Instead, these outer stars maintained a nearly constant speed, defying the predictions of visible mass distribution. This discrepancy suggested that galaxies are enshrouded in massive halos of dark matter, which provide the additional gravity needed to explain their behavior. These dark matter halos are not just peripheral components. They are the scaffolding upon which galaxies are built. Simulations of galaxy formation reveal that dark matter clumps together under its own gravity, creating dense regions that attract ordinary matter. Over billions of years, this ordinary matter cools, condenses, and ignites into stars, forming the luminous structures we observe. Without dark matter, the gravitational pull of baryonic matter alone would be insufficient to gather and stabilize the material needed to form galaxies. The influence of dark matter extends beyond individual galaxies to galaxy clusters, the largest gravitationally bound structures in the universe. These clusters, containing hundreds or even thousands of galaxies, are held together by the combined gravitational forces of their components. However, measurements of their total mass reveal a striking imbalance. The visible matter, including stars and hot gas, accounts for only about 15% of the mass required to explain the cluster's stability. The remaining mass is attributed to dark matter, which forms an invisible backbone anchoring these colossal structures. Gravitational lensing provides a powerful method for mapping the distribution of dark matter in galaxies and clusters. When light from a distant galaxy passes through a massive object, such as a galaxy cluster, the object's gravity bends the light, creating distorted or magnified images of the background source. By analyzing these distortions, scientists can determine the mass distribution of the lensing object. Time and again, these maps show that the bulk of the mass resides in dark matter, not in the visible components. Dark matter also plays a crucial role in the formation of galactic structures. Spiral galaxies, for instance, owe their iconic shapes to the interplay between their rotation and the gravitational influence of dark matter. The density waves within these galaxies, which create their spiral arms, are stabilized by the dark matter halo. Similarly, elliptical galaxies, often found in dense environments, result from the merging of smaller galaxies. These mergers are heavily influenced by the dark matter halos surrounding the colliding galaxies, which act as gravitational anchors, guiding the process. In dwarf galaxies, the role of dark matter is even more pronounced. These small, faint galaxies often have mass-to-light ratios far higher than their larger counterparts, indicating that dark matter constitutes the majority of their mass. Without the stabilizing influence of dark matter, these fragile systems would be easily disrupted by interactions with larger galaxies or the tidal forces of their host galaxy clusters. Despite its dominant role, dark matter does not act alone. It interacts with baryonic matter in complex ways, influencing star formation and galaxy evolution. For example, as dark matter halos grow and merge, they create gravitational wells that draw in gas. This gas cools and condenses into stars, but the process is not straightforward. Feedback mechanisms, such as supernova explosions and stellar winds, can eject gas from galaxies, slowing down star formation. Dark matter helps retain this ejected material, ensuring that it eventually returns to fuel future generations of stars. Even in the cosmic voids, the influence of dark matter is felt. These vast, empty regions of space, devoid of galaxies, are surrounded by filaments of dark matter that connect clusters and superclusters in a grand cosmic web. The dark matter within these filaments acts as a gravitational bridge, guiding the flow of galaxies and gas across the universe. As scientists continue to unravel the mysteries of dark matter, they face new questions. Why does dark matter clump into halos and filaments? Does it interact with itself? And if so, how does this influence galaxy formation? Could dark matter halos harbor their own complex structures, such as dense cores or subhalos, that impact their host galaxies? Simulations of dark matter behavior, run on supercomputers, provide glimpses into these possibilities. By modeling the formation of galaxies and clusters over billions of years, these simulations reveal the intricate dance of matter and gravity, highlighting the essential role of dark matter in shaping the universe. However, these models are only as good as the assumptions they are based on, and many questions remain unanswered. One of the most tantalizing mysteries is the potential connection between dark matter and the emergence of life. By influencing the formation of galaxies, stars, and planets, dark matter indirectly shapes the conditions necessary for life to arise. Its gravitational effects create the cosmic environments in which stars forge the elements of life, such as carbon, oxygen, and nitrogen. Without dark matter, the universe would be a far less hospitable place. Dark matter is not merely an invisible substance. It is the unseen conductor of a cosmic symphony. Its gravitational presence orchestrates the motion of galaxies, the formation of stars, and the evolution of the universe itself. Though we cannot see it, we live in its shadow, our existence shaped by its subtle, yet profound influence. As we journey further into the mysteries of dark matter, one question lingers. If this unseen force governs the cosmos so completely, what else might it reveal about the universe's hidden dimensions and the nature of reality itself? The birth of dark matter, its role in the early universe. To understand dark matter, we must journey back to the dawn of time, to the moments following the Big Bang. In this chaotic era, the universe was a hot, dense sea of particles and energy, expanding and cooling rapidly. As matter began to organize itself into the structures we see today, dark matter played a pivotal role, acting as an invisible framework for the cosmos. But how did this enigmatic substance originate, and what role did it play in shaping the universe from its earliest moments? The story of dark matter begins in the first fractions of a second after the Big Bang, during an epoch known as inflation. This brief but violent expansion stretched the fabric of space-time, magnifying quantum fluctuations into density variations across the universe. These tiny variations would later become the seeds of cosmic structure, but their growth depended on more than just ordinary matter. As the universe expanded and cooled, it transitioned from a plasma of quarks and gluons into a state where particles like protons and neutrons could form. During this time, a critical event known as baryogenesis occurred, establishing the imbalance between matter and antimatter that allowed the universe to exist as it does today. Yet, even with this imbalance, the amount of baryonic matter was insufficient to explain the observed structure of the cosmos. An additional, non-baryonic form of matter, dark matter, had to be present to amplify these density fluctuations. Unlike ordinary matter, dark matter does not interact with radiation, meaning it began to clump together much earlier in cosmic history. While baryonic matter remained coupled to radiation through electromagnetic interactions, dark matter moved freely under the influence of gravity. This early decoupling allowed dark matter to form the gravitational wells that would later attract ordinary matter, guiding the formation of galaxies, stars, and clusters. The cosmic microwave background, CMB, a relic of the universe's infancy, offers a snapshot of this critical period. The faint fluctuations in the CMB's temperature and polarization reveal the density variations that dark matter amplified. Without dark matter, these fluctuations would have been too small to form the large-scale structures we observe today. Its presence ensured that gravity had the power to overcome the smoothing effects of radiation pressure, enabling matter to clump together. As the universe continued to expand and cool, dark matter's influence became even more pronounced. Around 380,000 years after the Big Bang, the universe reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. This event, known as recombination, decoupled matter from radiation, allowing light to travel freely and creating the CMB we observe today. At this stage, baryonic matter began to fall into the gravitational wells created by dark matter, setting the stage for the formation of galaxies and stars. The first structures to emerge were small, dense regions of dark matter known as halos. These halos acted as cradles for the first stars, whose intense radiation and supernova explosions enriched the surrounding environment with heavier elements. This process of enrichment, repeated across billions of years, paved the way for the complex chemistry necessary for planet formation and life. Simulations of the early universe highlight the critical role of dark matter in shaping the cosmos. Without its gravitational influence, baryonic matter alone would have struggled to form the intricate web of filaments, clusters, and voids that define the large-scale structure of the universe. These simulations show how dark matter halos merge and grow over time, creating the scaffolding for galaxy formation and evolution. The properties of dark matter also determine the timeline of cosmic evolution. If dark matter were hot, consisting of fast-moving particles like neutrinos, it would have smoothed out density fluctuations, preventing the formation of structures on small scales. Instead, observations suggest that dark matter is cold, meaning its particles are slow-moving, allowing for the clumping necessary to form galaxies and clusters. This distinction between hot and cold dark matter is critical for understanding why the universe appears as it does today. As we examine the role of dark matter in the early universe, we encounter questions that challenge our understanding of physics. For instance, what processes during the Big Bang created dark matter particles? Some theories suggest that they formed as the universe cooled, transitioning through various phases of symmetry breaking that produced exotic particles. Others propose that dark matter originated from interactions in a higher dimensional space, spilling into our three-dimensional universe as a byproduct of these interactions. The interaction, or lack thereof, between dark matter and ordinary matter is another profound mystery. Why does dark matter seem to interact only through gravity? Could there be a dark sector of particles and forces that mirrors our own, hidden from view? These questions are not merely theoretical. Their answers could redefine our understanding of matter, energy, and the fundamental laws of the universe. The role of dark matter extends beyond its gravitational influence. Some theories suggest that it might have played a part in cosmic inflation itself, shaping the early universe's expansion. Others explore its potential interactions with dark energy, the force driving the accelerated expansion of the universe. These speculative ideas hint at a deeper connection between dark matter and the universe's most fundamental properties. The birth of dark matter is not just a story of the past. It is a continuing narrative that influences the cosmos even now. From the smallest galaxies to the largest clusters, dark matter remains a silent architect, shaping the universe in profound and mysterious ways. Its origins tie directly to the Big Bang, embedding it in the fabric of space-time and ensuring its role in cosmic evolution. As we delve deeper into the mysteries of dark matter, we must ask, what secrets of the universe are still encoded in its shadowy presence? Could understanding its birth reveal new insights into the nature of existence itself? The quest to answer these questions drives us to explore further, pushing the boundaries of knowledge and imagination. A dark symphony, gravitational lensing as a tool. The cosmos plays out like a symphony, where unseen forces shape its harmony and structure. Among these forces, dark matter stands as the silent conductor, directing the movement of galaxies and light across the vastness of space. To study this mysterious substance, scientists have harnessed one of nature's most extraordinary phenomena, gravitational lensing. By bending light through the fabric of space-time, gravitational lensing reveals the presence of dark matter, painting an intricate portrait of the invisible universe. But how does this cosmic tool work, and what has it taught us about dark matter? Gravitational lensing is rooted in Einstein's theory of general relativity, which describes gravity as the warping of space-time by mass. Massive objects like stars, galaxies, or galaxy clusters create a gravitational field that distorts the path of light passing nearby. This effect, much like a magnifying glass bending light rays, can amplify and distort the images of background objects, producing arcs, rings, or even multiple images. These distortions are not just fascinating to observe. They provide a direct measure of the mass causing the lensing, including any dark matter that might be present. One of the most famous examples of gravitational lensing is the Einstein ring, a complete circle of light formed when a distant galaxy or quasar is perfectly aligned behind a massive foreground object. These rings are rare, but when they occur, they provide an almost perfect map of the lensing mass, including both visible and dark matter. By analyzing the geometry and intensity of the light, scientists can reconstruct the mass distribution of the lensing object, offering a glimpse into the otherwise invisible dark matter halo. Gravitational lensing is categorized into three types: strong lensing, weak lensing, and microlensing. Each offers unique insights into the nature of dark matter. Strong lensing, like the Einstein rings, involves highly visible distortions and is often associated with massive galaxy clusters. These clusters, which contain thousands of galaxies and vast amounts of hot gas, also harbor dark matter halos that dominate their total mass. By studying these strong lensing events, astronomers can map the distribution of dark matter within the clusters, revealing its density and extent. Weak lensing, on the other hand, involves subtler distortions in the shapes of background galaxies. These distortions are caused by large-scale structures like cosmic filaments, which connect galaxy clusters across vast distances. Weak lensing surveys, such as those conducted by the Hubble Space Telescope or the Dark Energy Survey, measure these tiny shape changes statistically, building a comprehensive map of dark matter across the universe. These maps reveal the cosmic web, a vast network of dark matter filaments that underpins the distribution of galaxies and gas. Microlensing, the third type, occurs when a smaller mass, such as a star or a black hole, briefly magnifies the light of a background object. While microlensing is less effective for studying dark matter halos, it can reveal compact dark matter candidates like primordial black holes or massive compact halo objects, MACHOs. By analyzing microlensing events, scientists can constrain the fraction of dark matter that might exist in these exotic forms. One of the most compelling applications of gravitational lensing has been in studying galaxy clusters, such as the iconic Bullet Cluster. When two galaxy clusters collide, their dark matter halos pass through each other relatively undisturbed, while the visible matter, primarily hot gas, interacts and slows down. Gravitational lensing measurements of the Bullet Cluster show a clear separation between the mass associated with dark matter and the mass associated with ordinary matter, providing direct evidence for dark matter's existence and behavior. Another fascinating discovery comes from studying dark galaxies, regions of space where gravitational lensing reveals the presence of dark matter with little to no corresponding visible matter. These ghostly structures challenge our understanding of how galaxies form and evolve, suggesting that dark matter alone may sometimes fail to ignite star formation. Gravitational lensing has also played a crucial role in testing the nature of dark matter itself. By examining the density profiles of dark matter halos, scientists can determine whether dark matter behaves as a cold, collisionless substance or if it exhibits self-interactions. Observations of certain galaxy clusters show dark matter profiles consistent with the cold dark matter paradigm, where particles interact only through gravity. However, some anomalies suggest the possibility of self-interacting dark matter, opening new avenues for theoretical exploration. Advanced lensing techniques are now pushing the boundaries of what we can learn about dark matter. High-resolution imaging and adaptive optics allow astronomers to detect even the smallest distortions in light, enabling the study of dark matter substructures within larger halos. These substructures, or subhalos, could provide critical clues about the nature of dark matter particles and their clustering behavior. The role of dark matter in shaping the universe's evolution is further illuminated by gravitational lensing studies of the cosmic microwave background, CMB. As the CMB's photons travel through the universe, their paths are bent by the intervening matter, including dark matter. This lensing imprint on the CMB provides a complementary view of the large-scale distribution of dark matter, independent of visible structures like galaxies. Gravitational lensing not only maps the invisible, but also challenges the limits of our understanding. The precise measurements required for lensing studies demand cutting-edge technology, from space telescopes like the James Webb Space Telescope to future missions like Euclid and the Nancy Grace Roman Space Telescope. These instruments promise to refine our view of dark matter's role in the cosmos, revealing its behavior on scales both large and small. Yet, even as gravitational lensing illuminates the unseen, it raises profound questions. Why does dark matter cluster as it does? Could there be variations in its properties across different environments? Might lensing eventually uncover exotic forms of dark matter, or even hint at entirely new physical laws? Gravitational lensing is a testament to humanity's ingenuity, turning the universe's natural phenomena into tools of discovery. Through the bending of light, we have glimpsed the dark matter that shapes the cosmos, transforming the invisible into the observable. As we refine this cosmic tool, we move closer to unveiling the true nature of dark matter and the secrets it holds. The hunt begins. Experiments and observatories. Dark matter, elusive as it may be, has become the focus of one of science's most ambitious hunts. While its gravitational effects are undeniable, directly detecting or understanding its nature remains one of the greatest challenges in physics. Around the globe, experiments and observatories have been designed to illuminate this mystery. From deep underground laboratories to space-based telescopes, the tools of discovery are as innovative as the questions they aim to answer. How do we hunt for something that neither emits nor reflects light? And what have these efforts revealed so far? The search for dark matter can be divided into three main approaches: direct detection, indirect detection, and particle collider experiments. Each of these methods targets a different aspect of dark matter's possible interactions, and each relies on cutting-edge technology and creative problem-solving to explore the unknown. Direct detection experiments are designed to capture fleeting interactions between dark matter particles and ordinary matter. These interactions are predicted to be rare and incredibly subtle, requiring extraordinary sensitivity to detect. The most promising candidates for these interactions are weakly interacting massive particles, WIMPs, which might occasionally collide with atomic nuclei. Such collisions would produce tiny signals, such as a minuscule temperature increase or a faint burst of light, detectable under the right conditions. To minimize interference from cosmic rays and background radiation, direct detection experiments are conducted deep underground. Facilities like the Gran Sasso National Laboratory in Italy and the Sanford Underground Research Facility in the United States house massive detectors shielded by kilometers of rock. One prominent example is the LUX Zeppelin (LZ) experiment, which uses a tank filled with liquid xenon to detect the faint flashes of light produced when a WIMP interacts with a xenon atom. Although no definitive detections have been made yet, each experiment sets stricter limits on the properties of dark matter particles, narrowing the field for future searches. Indirect detection experiments take a different approach by searching for the byproducts of dark matter interactions. If dark matter particles can annihilate or decay, they might produce detectable signals such as gamma rays, neutrinos, or cosmic rays. Space-based observatories like the Fermi Gamma Ray Space Telescope and ground-based facilities like the Cherenkov Telescope Array are scanning the skies for these telltale emissions. The center of the Milky Way, where dark matter density is thought to be highest, has been a focal point for these searches. Unexplained gamma ray excesses in this region have sparked debate over whether they could be signals of dark matter annihilation or simply a result of more mundane astrophysical processes. Another intriguing target for indirect detection is the observation of dwarf galaxies orbiting the Milky Way. These galaxies are rich in dark matter, but contain relatively little ordinary matter, reducing the noise from other astrophysical sources. By studying these galaxies, scientists hope to uncover faint signals that might betray the presence of dark matter. Particle colliders like the Large Hadron Collider, LHC, offer a third avenue for exploring dark matter. By smashing protons together at near-light speeds, the LHC recreates conditions similar to those of the early universe, potentially producing dark matter particles in the process. Detectors surrounding the collision sites search for missing energy or momentum that could indicate the presence of invisible particles. While the LHC has yet to directly produce dark matter, it has placed stringent constraints on theoretical models and continues to refine our understanding of particle physics. In addition to these large-scale efforts, smaller and more speculative experiments are pushing the boundaries of what might be possible. Axion detection experiments, for instance, focus on identifying a different class of dark matter candidates. These hypothetical particles, much lighter than WIMPs, might interact with magnetic fields to produce weak electromagnetic signals. Projects like the Axion Dark Matter Experiment, ADMX, are tuning their instruments to detect these elusive signals, opening new frontiers in the search for dark matter. Meanwhile, astrophysical observatories play a crucial role in mapping the distribution of dark matter across the universe. Gravitational lensing, as explored in the previous chapter, allows scientists to chart the invisible halos surrounding galaxies and clusters. The Dark Energy Survey and future missions like Euclid and the Nancy Grace Roman Space Telescope are poised to create even more detailed maps of dark matter's influence on cosmic structures. Advanced simulations complement these observational efforts, modeling how dark matter behaves over billions of years. By comparing these simulations to real-world data, scientists can test theories about dark matter's properties and interactions. For example, discrepancies between simulations and observations have led to the exploration of self-interacting dark matter, a variant that could explain certain anomalies in galaxy formation. Despite decades of effort, the hunt for dark matter remains a story of persistence and innovation. Each null result is not a failure, but a step forward, eliminating possibilities and sharpening the focus of future searches. The stakes are high. Discovering dark matter would not only solve a fundamental mystery of the universe, but also open the door to entirely new physics. What if dark matter is not a single particle, but a spectrum of particles, like those in the Standard Model? What if it interacts with itself or forms structures beyond our current understanding? These questions drive scientists to push the limits of their instruments and imaginations. The search for dark matter is more than a scientific endeavor. It is a testament to humanity's determination to uncover the truth about the cosmos. Whether deep underground, in the vastness of space, or in the controlled chaos of particle collisions, the hunt for dark matter is a journey into the unknown, a journey that promises to reshape our understanding of the universe. Beyond the Standard Model, physics in crisis. The search for dark matter is more than just a hunt for an elusive particle. It is a test of the very foundations of physics. The inability to directly detect dark matter despite overwhelming evidence for its existence has placed modern physics at a crossroads. The Standard Model, our most successful framework for understanding the universe at the smallest scales, cannot explain dark matter. This crisis has sparked a revolution, pushing scientists to explore bold new theories and reimagine the laws of nature. How did we arrive at this impasse? And what lies beyond the Standard Model? The Standard Model of particle physics is a masterpiece, describing the fundamental particles and forces that govern the universe. It explains the behavior of electrons, quarks, photons, and even the Higgs boson, the particle that gives mass to others. Yet, as powerful as the Standard Model is, it accounts for only about 5% of the universe. The remaining 95%, dark matter and dark energy, is beyond its scope, revealing its limitations. One of the key reasons the Standard Model falls short is that it provides no candidate for dark matter. The known particles, like protons, neutrons, and neutrinos, do not possess the right properties to explain dark matter's behavior. Neutrinos, for example, are incredibly light and interact only weakly with matter, but they move too fast to account for the observed clustering of dark matter on cosmic scales. A new type of particle is needed, one that interacts gravitationally and perhaps weakly with ordinary matter, but remains otherwise invisible. This realization has led physicists to propose extensions to the Standard Model, the most prominent of which is supersymmetry. Supersymmetry posits that every particle in the Standard Model has a heavier superpartner. These superpartners could include candidates for dark matter, such as the neutralino, a WIMP that interacts only weakly and could account for the missing mass of the universe. Supersymmetry also has the added benefit of resolving other mysteries, such as the unification of forces at high energies and the stability of the Higgs boson. Despite its elegance, however, supersymmetry has yet to be confirmed experimentally, and the failure to detect superpartners at the Large Hadron Collider has raised doubts about its viability. Another intriguing extension of the Standard Model is the idea of extra dimensions. Inspired by string theory, which seeks to unify quantum mechanics and gravity, these models suggest that dark matter could be a manifestation of particles in higher dimensional spaces. In our three-dimensional universe, these particles might appear as invisible matter with only gravitational interactions. Experiments like those at the LHC are probing these possibilities by searching for missing energy and other anomalies that could hint at extra dimensions. The crisis deepens when we consider alternative approaches, such as modifications to gravity itself. Modified Newtonian dynamics, MOND, and similar theories propose that the laws of gravity change at large scales, eliminating the need for dark matter. While MOND can explain certain galactic phenomena, it struggles to account for the behavior of galaxy clusters and the large-scale structure of the universe. Moreover, observations like the Bullet cluster, which show clear separation between visible matter and gravitational mass, strongly favor the existence of dark matter over modifications to gravity. Compounding these challenges is the question of why dark matter seems to interact only through gravity. Could there be a dark sector of particles and forces, analogous to the particles and forces we observe, but hidden from view? If such a dark sector exists, it might contain not just dark matter particles but also dark radiation, dark electromagnetism, and even dark stars and planets. Exploring this possibility requires innovative experiments that push the boundaries of current technology. The crisis has also reignited interest in more exotic theories. One such idea is the concept of sterile neutrinos, which are heavier cousins of the known neutrinos and interact only through gravity. These particles could account for certain anomalies in astrophysical observations, such as the unusual behavior of dwarf galaxies. Other theories propose entirely new forms of matter, like axions, which are ultralight particles that might behave more like waves than particles. Axions could solve not only the dark matter mystery, but also other problems in quantum physics, such as the strong CP problem. The implications of dark matter extend beyond particle physics to cosmology. The lambda-cold dark matter, lambda CDM, model, our best description of the universe's evolution, relies on the existence of cold dark matter to explain the formation of galaxies and the large-scale structure. If dark matter does not exist as we currently understand it, the entire framework of lambda CDM could be called into question. This would force a radical rethinking of how the universe began and evolved over billions of years. The crisis has also driven innovation in experimental techniques. Detectors are now capable of unprecedented sensitivity, probing interactions so rare that they occur less than once per year in massive underground facilities. Particle colliders are exploring higher energy regimes, searching for signs of new physics that might point to dark matter. Even astrophysical observations, such as those of gravitational lensing and cosmic background radiation, are being used to test theories about the distribution and behavior of dark matter. As the search continues, one question looms large. What if dark matter is not a particle at all? Some theories suggest it might be a field, similar to the Higgs field, that permeates the universe and exerts gravitational effects. Others propose that dark matter might be an emergent phenomenon, arising from unknown interactions in space-time itself. These ideas challenge not just the standard model, but also the very foundations of physics, opening doors to entirely new paradigms. The crisis of dark matter is not a failure, but an opportunity, a chance to push the boundaries of knowledge and uncover the deeper truths of the universe. It is a reminder that science is a process of discovery, where each unanswered question leads to new horizons. As we stand on the brink of these discoveries, the hunt for dark matter promises to reshape not only physics but also our understanding of existence itself. Quantum shadows, possible connections to quantum mechanics. As the search for dark matter continues, it becomes clear that unraveling its mysteries may require us to probe the quantum realm, where reality defies intuition. Quantum mechanics, the framework governing the behavior of particles at the smallest scales, has given us tools to explore the universe's most fundamental aspects. But could dark matter, with its elusive and enigmatic nature, be linked to the quantum world? Might quantum mechanics hold the key to understanding this invisible force? Quantum mechanics introduces phenomena so strange they border on the surreal. Particles exist as waves of probability, only taking definitive positions when observed. They can also become entangled, influencing each other instantaneously over vast distances, and they exhibit behaviors that seem to defy classical logic. These principles, though thoroughly tested, remain mysterious and open questions about the nature of reality itself. One tantalizing connection between dark matter and quantum mechanics involves the concept of wave-particle duality. If dark matter is made up of particles, those particles could also exhibit wave-like properties. This duality might explain some of the peculiarities in dark matter's behavior, such as its inability to clump on small scales or form dense cores within galaxies. In this view, dark matter could consist of ultralight particles with wavelengths so large that they create quantum interference patterns, smoothing out their distribution across space. This idea has gained traction with theories involving axions, hypothetical particles that are both lightweight and abundant. Axions, unlike traditional particle candidates like WIMPs, could behave more like waves than particles. Their collective oscillations might form structures similar to Bose-Einstein condensates, a state of matter where particles act as a single quantum entity. If dark matter is composed of axions, its quantum nature might become apparent through subtle effects on the rotation of galaxies or the propagation of light through magnetic fields. Quantum mechanics also invites speculation about the role of virtual particles in the behavior of dark matter. Virtual particles, which pop in and out of existence in the quantum vacuum, contribute to phenomena like the Casimir effect and the Lamb shift. Some theories suggest that dark matter might interact with virtual particles in ways that have yet to be observed. This interaction could explain why dark matter does not interact with electromagnetic forces, yet influences gravity on cosmic scales. Another intriguing possibility is that dark matter could be linked to hidden dimensions predicted by string theory and related frameworks. String theory posits that the universe contains additional spatial dimensions beyond the familiar three, which are compactified and invisible to us. Dark matter might exist as particles or fields confined to these hidden dimensions, manifesting in our universe only through gravitational interactions. These higher-dimensional theories are inherently quantum mechanical, relying on the principles of quantum field theory to describe the behavior of particles and forces in multidimensional space. Quantum entanglement, a phenomenon where particles become interconnected in ways that defy classical physics, offers another speculative avenue for understanding dark matter. Could dark matter particles be entangled across vast cosmic distances, forming a hidden web of quantum correlations? Such a network might influence the distribution of dark matter and its interactions with ordinary matter. While highly speculative, this idea aligns with the growing realization that quantum phenomena may extend far beyond the microscopic scale. One of the most profound connections between dark matter and quantum mechanics lies in the question of gravity. General relativity, our best theory of gravity, is fundamentally classical, while quantum mechanics governs the subatomic world. The two frameworks have resisted unification for decades, but dark matter might provide a bridge between them. If dark matter consists of particles that interact gravitationally, but not electromagnetically, studying these interactions could offer clues about the quantum nature of gravity itself. The holographic principle, a concept derived from quantum mechanics and string theory, further deepens this connection. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram. Dark matter might play a role in this encoding process, its gravitational effects reflecting deeper quantum properties of the universe. If true, this would mean that dark matter is not just a physical substance, but a manifestation of the universe's underlying quantum structure. Experimental efforts to explore these ideas are still in their infancy, but are rapidly advancing. Quantum sensors, such as atomic clocks and interferometers, are being adapted to search for ultralight dark matter. These sensors are capable of detecting minute changes in gravitational fields or the passage of waves created by dark matter interactions. Similarly, experiments like ADMX and CASPER are hunting for axions by looking for their effects on electromagnetic fields. The implications of a quantum connection to dark matter are staggering. If dark matter is fundamentally quantum in nature, its discovery would open an entirely new frontier in physics. It could shed light on unresolved mysteries, such as the nature of space-time, the origins of the universe, and the true fabric of reality. At the heart of this inquiry lies a profound question. Is dark matter a clue to a deeper unity between the quantum and cosmic scales? Could understanding its nature lead to a theory of everything, bridging the gap between general relativity and quantum mechanics? The answers may lie in the interplay of particles, waves, and dimensions, a dance as intricate and mysterious as the universe itself. As we delve deeper into the quantum shadows of dark matter, we are reminded that the universe is far stranger and more complex than we ever imagined. In the hidden interplay of forces and particles, we glimpse the profound beauty of a cosmos waiting to reveal its secrets. Dark matter versus dark energy, two different mysteries. The universe is a vast and intricate puzzle, where two of the most enigmatic pieces, dark matter and dark energy, play distinct but equally crucial roles. These cosmic phenomena dominate the universe, yet their natures and effects are fundamentally different. While dark matter holds galaxies together with its gravitational pull, dark energy drives them apart, fueling the accelerated expansion of the cosmos. What are these two forces, and how do they coexist in shaping the universe? To understand the relationship between dark matter and dark energy, it's essential to first examine their contrasting roles. Dark matter, as discussed in earlier chapters, is the invisible mass that provides the gravitational glue holding galaxies, galaxy clusters, and the cosmic web together. Its presence is inferred from the way it bends light, influences galaxy rotations, and sculpts the large-scale structure of the universe. In contrast, dark energy is the mysterious force driving the accelerated expansion of the universe. Its existence was first inferred in 1998, when observations of distant Type Ia supernovae revealed that galaxies were not only moving away from us, but doing so at an increasing rate. This discovery was a shock to cosmologists, as it implied the existence of a force counteracting gravity on the largest scales. Dark energy is thought to comprise approximately 68% of the universe, making it the dominant component of the cosmic pie. Dark matter accounts for about 27%, while ordinary matter, the stars, planets, and galaxies we can see, makes up a mere 5%. Together, dark matter and dark energy govern the universe's fate, pulling it in opposing directions. While their effects are well documented, the fundamental nature of both dark matter and dark energy remains elusive. Dark matter is widely believed to consist of particles that interact only weakly with ordinary matter, whereas dark energy might be a property of space itself. The leading theory for dark energy is the cosmological constant, introduced by Einstein as a term in his equations of general relativity. This constant represents the energy density of empty space, which remains constant as the universe expands. However, the cosmological constant is not the only explanation for dark energy. Some theories propose that dark energy could arise from a dynamic field, dubbed quintessence, which changes over time. Others suggest it might result from modifications to gravity on large scales, akin to alternatives proposed for dark matter. Despite their differences, dark matter and dark energy share some intriguing connections. Both are invisible, detectable only through their effects on the cosmos. Both challenge the limits of the standard model of particle physics and require extensions to our understanding of fundamental forces. And both are essential for explaining the universe's evolution, from its earliest moments to its far future. One of the most profound links between dark matter and dark energy lies in their impact on the universe's large-scale structure. In the early universe, dark matter dominated, clumping together to form the seeds of galaxies and clusters. Its gravitational pull counteracted the universe's initial expansion, slowing it down. Dark energy, however, took over as the universe aged, driving its accelerated expansion and stretching the fabric of space-time. This cosmic tug-of-war has shaped the universe into what we see today. Interestingly, dark matter and dark energy also appear to influence the same phenomena in different ways. For instance, dark matter's gravitational effects are evident in the bending of light around massive objects, known as gravitational lensing. Dark energy, too, can affect gravitational lensing, as the accelerated expansion it drives alters the distances between objects and the paths of light rays. Observing these subtle differences provides critical clues about the nature of both phenomena. Another area of overlap is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB encodes information about the universe's composition and expansion history. Dark matter's influence can be seen in the way it shaped the density fluctuations that later became galaxies, while dark energy's role is evident in the overall geometry of the universe. Together, these effects allow scientists to study both dark matter and dark energy using the same data sets. The interplay between dark matter and dark energy also raises profound questions about the universe's ultimate fate. If dark energy continues to dominate, the universe will keep expanding at an ever-accelerating rate. Galaxies will drift farther apart, stars will burn out, and the cosmos will fade into a cold, dark void, a scenario known as the Big Freeze. However, if dark energy's influence weakens over time, gravitational forces might regain control, leading to a collapse of the universe in a big crunch. Understanding the precise nature of dark matter and dark energy is essential for predicting which scenario will prevail. Despite the progress made in studying these phenomena, their origins remain deeply mysterious. Why do dark matter and dark energy exist at all? Are they distinct entities, or could they be manifestations of the same underlying phenomenon? Some theories propose that dark matter and dark energy are connected through yet undiscovered physics. For example, dark energy might interact with dark matter in subtle ways, influencing its distribution or behavior. Other theories suggest that both could arise from modifications to gravity or the properties of spacetime. The tools used to study dark matter and dark energy are continually advancing. Large-scale surveys like the Dark Energy Survey and the upcoming Euclid mission are mapping the universe in unprecedented detail, providing new insights into the interplay between these forces. Experiments like those at the Large Hadron Collider are probing for dark matter particles, while telescopes and satellites continue to refine measurements of dark energy's effects. As we delve deeper into the mysteries of dark matter and dark energy, we confront the limits of human knowledge and imagination. These forces challenge our understanding of physics, cosmology, and the nature of existence itself. Yet, they also inspire us to push the boundaries of science, to seek answers to questions that lie at the heart of the universe. The story of dark matter and dark energy is far from complete, but it is one of the most profound and exciting narratives in modern science. By exploring these twin mysteries, we move closer to understanding the cosmos and our place within it. The dark web, cosmic filaments, and the large-scale structure. The universe is not a random scattering of galaxies and stars. It is an intricately woven tapestry of structures interconnected by invisible threads. At the heart of this cosmic architecture lies dark matter, forming a vast and unseen web that guides the distribution of galaxies, clusters, and superclusters. This dark web is a foundational element of the cosmos, shaping its large-scale structure and influencing the evolution of everything within it. But what is the nature of this web, and how does it reveal the hidden workings of the universe? When we peer into the cosmos on the grandest scales, a striking pattern emerges. Galaxies are not evenly spread through space. They cluster along vast filaments that stretch for hundreds of millions of light years. These filaments connect massive galaxy clusters, forming a web-like structure with enormous voids in between. This network, known as the cosmic web, is the result of billions of years of gravitational interactions, driven primarily by dark matter. The cosmic web began to form shortly after the Big Bang, during a period when the universe was a nearly uniform soup of matter and energy. Tiny fluctuations in the density of this primordial soup, amplified by dark matter's gravitational pull, seeded the development of large-scale structures. Over time, dark matter clumped into dense regions, creating a scaffolding for ordinary matter to follow. This process allowed galaxies and clusters to form along the filaments of the cosmic web, while voids grew emptier as matter was pulled toward denser regions. Dark matter plays a crucial role in the formation and maintenance of the cosmic web. Unlike ordinary matter, which interacts through electromagnetic forces and can lose energy through radiation, dark matter interacts only gravitationally. This lack of interaction allows it to move freely, creating dense halos that attract ordinary matter. These halos are the birthplaces of galaxies, which form as baryonic matter cools and condenses within the gravitational wells carved out by dark matter. Simulations of the universe's evolution, such as those run by the Millennium Simulation Project, vividly illustrate the emergence of the cosmic web. These simulations start with conditions derived from the cosmic microwave background and track the behavior of dark matter and ordinary matter over billions of years. The resulting maps reveal a stunningly intricate network of filaments, clusters, and voids, matching observations from telescopes and surveys. One of the most remarkable features of the cosmic web is its scale. The filaments can stretch for hundreds of millions of light years, connecting galaxy clusters separated by vast distances. These clusters, some containing thousands of galaxies, are among the largest structures in the universe. In contrast, the voids between the filaments are some of the emptiest regions in space, often spanning tens of millions of light-years with only a few isolated galaxies scattered within them. The cosmic web is not just a passive structure. It actively shapes the evolution of galaxies and clusters. Galaxies within filaments experience different environments than those in voids, leading to variations in their properties. For example, galaxies in dense regions often interact and merge more frequently, driving rapid star formation and the growth of supermassive black holes. In contrast, galaxies in voids tend to evolve more slowly, isolated from the gravitational influences of nearby structures. Gravitational lensing has become an invaluable tool for studying the cosmic web. By analyzing the way light from distant galaxies is bent as it passes through massive structures, astronomers can map the distribution of dark matter in unprecedented detail. These maps reveal not only the locations of the filaments, but also their density and how they connect galaxy clusters across vast distances. The cosmic web also offers a unique laboratory for testing theories about dark matter and cosmology. By comparing observations of the web structure to predictions from simulations, scientists can refine their understanding of dark matter's properties. For instance, the cold nature of dark matter, its tendency to form dense clumps rather than disperse widely, explains the web-like pattern observed in the universe. However, deviations from this pattern could hint at alternative models, such as warm dark matter or self-interacting dark matter. One of the most intriguing aspects of the cosmic web is its role in the flow of matter across the universe. Galaxies and clusters are not static. They move along the filaments under the influence of gravity, merging and growing over time. This flow creates a dynamic system where the cosmic web itself evolves, with filaments becoming denser and voids expanding as matter is pulled inward. Despite its importance, the cosmic web remains largely hidden from view. While we can observe the galaxies and clusters that trace its filaments, the underlying dark matter remains invisible. However, new techniques are beginning to reveal the web more directly. For example, studies of the intergalactic medium, the gas that fills the spaces between galaxies, can provide indirect evidence of the web structure. By analyzing the absorption lines in the spectra of distant quasars, astronomers can map the distribution of this gas and infer the presence of the filaments. Future missions and instruments promise to deepen our understanding of the cosmic web. The upcoming Euclid mission and the Vera-C-Rubin Observatory will conduct large-scale surveys of the universe, mapping the distribution of galaxies and dark matter with unprecedented precision. These surveys will not only illuminate the structure of the web, but also provide critical insights into the nature of dark matter and dark energy. The cosmic web is more than just a structure. It is a story, a record of the universe's evolution over billions of years. It reflects the interplay between dark matter, gravity, and the laws of physics, offering a glimpse into the forces that shape reality on the grandest scales. As we continue to explore this hidden network, we come closer to understanding the true nature of the cosmos and our place within its vast and intricate tapestry. Simulating the invisible, computer models of dark matter. How do we study something we cannot see, touch, or directly detect? For scientists seeking to understand dark matter, the answer lies in simulation. Using powerful supercomputers and advanced algorithms, researchers create virtual universes where dark matter can be modeled, tested, and analyzed. These simulations are not mere approximations. They are detailed, data-driven reconstructions of how dark matter behaves on both cosmic and galactic scales. What have these models revealed about the invisible universe, and how do they shape our understanding of dark matter? The story of dark matter simulations begins with the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. Observations of the CMB provide a snapshot of the universe when it was just 380,000 years old, revealing the distribution of matter at that time. These density fluctuations, encoded in the CMB, serve as the initial conditions for simulations of the universe's evolution. By inputting this data into computer models, scientists can track how dark matter and ordinary matter interact under the influence of gravity, forming the large-scale structure we observe today. One of the most famous examples of such a simulation is the Millennium Simulation, conducted in 2005. This groundbreaking project modeled the evolution of the universe over billions of years, tracking the behavior of dark matter and its role in shaping galaxies and clusters. Using over 10 billion particles to represent dark matter, the simulation revealed the formation of the cosmic web, an intricate network of filaments, nodes, and voids that mirrors real observations of the universe. The success of the Millennium Simulation validated the cold dark matter (CDM) paradigm, which posits that dark matter consists of slow-moving particles that clump together under gravity. More recent simulations, such as the Illustrious and Eagle projects, have taken these efforts to new heights. These models incorporate not only dark matter, but also baryonic processes like star formation, supernova explosions, and the effects of black holes. By including these additional factors, scientists can better understand how dark matter interacts with ordinary matter to create the diverse structures we see in the universe, from spiral galaxies to elliptical clusters. One key insight from simulations is the role of dark matter in galaxy formation. Without dark matter, galaxies would struggle to form. Simulations show that dark matter halos act as gravitational wells, pulling in gas that eventually cools and condenses into stars. These halos provide the stability needed for galaxies to survive over billions of years, even as they interact and merge with one another. The size, shape, and density of a dark matter halo can significantly influence the properties of the galaxy it hosts, determining factors like its rotation curve and star formation rate. Simulations also shed light on the behavior of dark matter on smaller scales, where its properties become more apparent. For instance, models predict the existence of subhalos, smaller clumps of dark matter orbiting within larger halos. These subhalos are thought to be the remnants of smaller galaxies that were absorbed into larger systems, and they could explain some of the anomalies observed in galaxy rotation curves. However, detecting these subhalos remains a challenge, as they are composed entirely of dark matter and emit no light. Another area where simulations have been invaluable is in testing different dark matter models. While the standard cold dark matter model has been successful in explaining many aspects of the universe, it does have limitations. For example, it struggles to account for the observed distribution of dark matter in the centers of galaxies, where simulations predict denser cores than those observed. This discrepancy, known as the core-cusp problem, has led to alternative models such as warm dark matter, WDM, and self-interacting dark matter, SIDM. Warm dark matter consists of lighter, faster-moving particles that do not clump as tightly as cold dark matter, resulting in less dense galactic cores. Self-interacting dark matter, on the other hand, posits that dark matter particles can collide with one another, redistributing energy and softening the density of cores. Simulations incorporating these models have shown promise in resolving some of the discrepancies between theory and observation, but further data is needed to confirm their validity. The role of supercomputers in dark matter research cannot be overstated. Modern simulations require immense computational power to model the behavior of billions of particles over cosmic timescales. Facilities like Oak Ridge National Laboratory and CERN host some of the most advanced supercomputers in the world, capable of running simulations that generate petabytes of data. These simulations are not only computationally intensive, but also require sophisticated algorithms to accurately represent the complex interactions between dark matter, baryonic matter, and gravity. As simulations grow more sophisticated, they are also becoming more precise. Observations from telescopes like the James Webb Space Telescope and future missions like Euclid provide increasingly detailed data on the distribution of galaxies, clusters, and dark matter. By comparing these observations to simulations, scientists can refine their models, narrowing down the properties of dark matter and testing new theories. One of the most exciting frontiers in simulation is the integration of artificial intelligence and machine learning. These technologies can analyze vast datasets generated by simulations, identifying patterns and correlations that might otherwise go unnoticed. Machine learning algorithms are also being used to speed up the simulation process, allowing researchers to explore a wider range of parameters and scenarios. Simulating the invisible is not just about understanding dark matter. It is about unraveling the fundamental laws of the universe. By modeling how dark matter interacts with ordinary matter, gravity, and even itself, simulations provide a window into the processes that shape reality on the grandest scales. They allow us to test theories, predict observations, and explore scenarios that would be impossible to replicate in the laboratory. As we continue to refine these models, one question looms large. Could the universe itself be a kind of simulation, governed by underlying principles that we are only beginning to grasp? While this idea remains speculative, it underscores the profound connection between the tools we use to study the universe and the nature of the universe itself. The journey to understand dark matter is as much a quest for knowledge as it is a testament to human ingenuity. Through simulations, we bring the invisible into focus, transforming abstract theories into tangible insights. In the dance of particles and forces, we glimpse the hidden architecture of the cosmos, a structure woven by the silent, unseen hand of dark matter. The galactic halo, a hidden domain of dark matter. Dark matter is not evenly distributed throughout the universe. Instead, it forms structures that influence the behavior of galaxies and the stars within them. One of the most intriguing manifestations of dark matter is the galactic halo, a vast, invisible sphere that envelopes galaxies like a ghostly cocoon. This halo is a cornerstone of our understanding of dark matter, shaping the dynamics of galaxies and their evolution. But what exactly is a galactic halo, and what secrets does it hold about the elusive nature of dark matter? A galactic halo extends far beyond the visible boundaries of a galaxy. In a spiral galaxy like the Milky Way, the bright, disc-shaped region of stars and gas is surrounded by a nearly spherical halo of dark matter. This halo does not emit, absorb, or reflect light, making it invisible to telescopes. However, its gravitational effects are unmistakable, revealing its presence through the motions of stars and gas within the galaxy. One of the earliest clues to the existence of dark matter halos came from the study of galactic rotation curves. In the 1970s, astronomer Vera Rubin and her colleagues measured the speeds of stars orbiting the centers of spiral galaxies. They found that stars at the edges of these galaxies were moving much faster than expected based on the visible mass alone. According to Newtonian physics, the orbital speed should decrease with distance from the galactic center, similar to how planets farther from the Sun move more slowly. Instead, the speeds remain nearly constant, implying the presence of an unseen mass, dark matter, extending well beyond the luminous disk. The galactic halo provides the additional gravitational pull needed to explain these flat rotation curves. Without it, the outer stars would not have enough gravitational binding to remain in orbit, and the galaxy would fly apart. The halo's mass is so substantial that it often outweighs the visible matter in the galaxy by a factor of 5 or more. The structure of a galactic halo is complex and multilayered. At its core, the halo may contain substructures, such as clumps or streams of dark matter. These subhalos are thought to be remnants of smaller galaxies or dark matter structures that merged with the host galaxy over time. Observations of stellar streams, long, thin trails of stars that were once part of smaller galaxies, offer indirect evidence for these subhalos. As these smaller systems are torn apart by gravitational forces, their stars are spread out along orbits within the halo, while the dark matter merges with the larger halo. The outer regions of the halo extend far beyond the visible galaxy, forming a diffuse, spherical cloud. This region is less dense but still exerts a significant gravitational influence on the galaxy's dynamics and its interactions with neighboring galaxies. The extent of the halo can be difficult to determine, but it is estimated to stretch hundreds of thousands of light-years from the galactic center. Understanding the composition of dark matter halos is one of the most pressing questions in astrophysics. Are they composed entirely of cold dark matter, as the standard cosmological model suggests? Or do they also contain contributions from alternative forms of dark matter, such as self-interacting dark matter or axions? The behavior of halos, particularly their density profiles and substructure, provides critical clues for testing these theories. Simulations have played a key role in exploring the properties of galactic halos. Using supercomputers, researchers model the formation and evolution of dark matter halos over billions of years. starting from the density fluctuations present in the early universe. These simulations show how dark matter halos grow through a process of hierarchical clustering, in which smaller structures merge to form larger ones. They also reveal the intricate network of filaments and voids that connect halos across the cosmic web. Observations of satellite galaxies orbiting the Milky Way provide additional insights into the structure of our own galactic halo. These dwarf galaxies, such as the Magellanic Clouds, are embedded within the Milky Way's dark matter halo and interact with it gravitationally. By studying their motions and distribution, astronomers can infer the halo's mass and shape. Recent discoveries of faint, ultra-diffuse galaxies have further expanded our understanding of these interactions, suggesting that the halo may contain far more substructure than previously thought. The study of galactic halos also has implications for the broader questions of cosmology. For example, the abundance and distribution of dark matter halos across the universe provide a critical test for the cold dark matter model. If observations deviate from predictions, such as finding fewer subhalos than expected, it could point to new physics or alternative explanations for dark matter's behavior. Another intriguing aspect of galactic halos is their role in galaxy formation and evolution. The interaction between a halo and the ordinary matter it surrounds determines how galaxies grow and change over time. Halos provide the gravitational wells that draw in gas, which cools and condenses to form stars. However, the properties of the halo, such as its density and temperature, also influence processes like star formation, feedback from supernovae, and the growth of central supermassive black holes. Despite their importance, dark matter halos remain enigmatic. Their invisible nature makes them challenging to study directly, and many questions about their composition and dynamics remain unanswered. For example, why do some halos appear to lack a dense core, contrary to theoretical predictions? What role do dark matter halos play in the mysterious phenomenon of galactic spin? And how do halos interact with the elusive dark energy that drives the universe's accelerated expansion? To answer these questions, astronomers are turning to next-generation observatories and advanced techniques. Instruments like the Vera-C Rubin Observatory and space missions like Euclid will provide unprecedented maps of the universe's dark matter distribution, offering new insights into the structure and behavior of galactic halos. At the same time, experiments searching for direct and indirect evidence of dark matter particles will help constrain the properties of the material that makes up these halos. Galactic halos are more than just repositories of dark matter. They are dynamic, evolving systems that hold the key to understanding the universe's invisible architecture. By studying them, we gain not only a deeper understanding of dark matter, but also a richer perspective on the forces that shape the cosmos. As our tools and theories continue to evolve, the hidden domain of dark matter halos may finally come into view, revealing the secrets of the unseen universe. Collisions in the void, dark matter, and galaxy mergers. The universe is in constant motion, a dynamic interplay of forces and structures that create and reshape its contents. Among the most spectacular and consequential events in this cosmic ballet are galaxy mergers, massive collisions that bring together stars, gas, and dark matter in a gravitational embrace. These mergers are not merely dramatic. They are crucial to the evolution of galaxies and the large-scale structure of the universe. But what role does dark matter play in these titanic encounters? How does it shape the outcomes of such collisions? And what can we learn about its properties through these events? Galaxy mergers occur when two or more galaxies come close enough for their mutual gravitational forces to dominate over the expansion of the universe. These interactions can take billions of years to complete, but their effects are profound. Stars, which are relatively far apart within galaxies, rarely collide directly. Instead, the gravitational forces during a merger disrupt the orbits of stars, gas clouds, and other matter, creating tidal streams, distortions, and sometimes entirely new structures. Dark matter, which constitutes the majority of a galaxy's mass, governs much of what happens during a merger. Unlike stars and gas, which can lose energy and settle into new orbits, dark matter interacts only through gravity. This fundamental difference leads to intriguing behaviors that reveal its presence and properties. One of the most famous examples of dark matter's role in galaxy mergers is the Bullet Cluster, a system of two colliding galaxy clusters. Observations of the Bullet Cluster show a striking separation between the visible matter, mostly hot gas detected through X-ray emissions, and the total gravitational mass measured via gravitational lensing. The visible gas from the two clusters collided and slowed down due to friction, while the dark matter passed through the collision largely unimpeded. This separation provides compelling evidence that dark matter does not interact with itself or with ordinary matter in the same way, supporting the idea that it interacts only gravitationally. Galaxy mergers are also critical for studying the distribution of dark matter within galactic halos. As galaxies collide, their dark matter halos interact gravitationally, influencing the dynamics of the merger. Simulations of these events show that dark matter halos can become stretched and distorted, creating long tidal tails and streams. These features, while invisible, influence the visible components of the galaxy, such as stars and gas, shaping the final structure after the merger. Dark matter also plays a role in triggering star formation during mergers. When galaxies collide, their gas clouds can be compressed, igniting bursts of star formation known as starbursts. The distribution and density of the dark matter halo can affect how this gas behaves, influencing the duration and intensity of star formation. In some cases, the merger can funnel gas toward the galactic center, fueling the growth of supermassive black holes and the activation of quasars. On larger scales, mergers between galaxy clusters provide a laboratory for understanding dark matter's behavior. These colossal collisions involve not only individual galaxies, but also the vast dark matter halos surrounding them. As clusters merge, their dark matter halos interact in ways that can reveal clues about the nature of dark matter. For instance, if dark matter particles have a small degree of self-interaction, these collisions might produce subtle differences in the distribution of dark matter compared to non-interacting models. Observing such effects could help narrow down the properties of dark matter particles. Simulations of galaxy and cluster mergers are vital for interpreting these observations. Using supercomputers, scientists can model the interactions between stars, gas, and dark matter over billions of years, reproducing the complex dynamics of mergers. These simulations help researchers understand the gravitational effects of dark matter and test different theories about its properties. For example, models incorporating self-interacting dark matter can predict slightly different outcomes for mergers, such as the distribution of mass or the shapes of tidal streams. Dark matter's role in mergers is not limited to the immediate collision. Over time, the merging process redistributes matter, influencing the long-term evolution of the resulting galaxy or cluster. Dark matter halos, which often contain subhalos, can create ripples in the gravitational potential, affecting the orbits of stars and gas for billions of years. This ongoing interaction can shape the structure of the galaxy, creating features like extended halos, faint stellar streams, or elongated shapes. The study of galaxy mergers has also raised new questions about dark matter's role in the universe. For instance, why do some galaxies retain much of their dark matter after a merger, while others appear to lose a significant portion? Could this discrepancy hint at variations in the nature of dark matter or differences in the environments of the merging galaxies? These questions drive ongoing research, pushing the boundaries of what we know about dark matter and its behavior. Galaxy mergers are not just catastrophic events, they are also creative ones. They can give rise to new galaxies, fuel the formation of stars, and drive the growth of supermassive black holes. Dark matter is central to all of these processes, shaping the outcomes in ways we are only beginning to understand. By studying these events, astronomers gain insights into both the visible and invisible components of the universe. The future of galaxy merger research looks promising, with new instruments and missions poised to provide unprecedented data. Observatories like the James Webb Space Telescope will enable detailed studies of mergers in the distant universe, where the effects of dark matter might be observed in early galaxy formation. Surveys from the Rubin Observatory will map the distribution of dark matter in and around merging systems, offering new clues about its properties. Ultimately, Galaxy mergers are windows into the fundamental workings of the cosmos. Through these cosmic collisions, we can glimpse the hidden dynamics of dark matter, uncovering the invisible forces that shape the universe. As we continue to explore these events, we move closer to understanding the nature of dark matter and its profound influence on the fabric of reality. The bullet cluster, proof in the sky. Among the myriad phenomena in the universe, few have provided as compelling evidence for the existence of dark matter as the bullet cluster. This unique cosmic collision between two galaxy clusters has become a cornerstone of modern astrophysics, showcasing the power of gravitational lensing and the stark differences between dark matter and ordinary matter. What makes the bullet cluster such a striking example of dark matter's influence, and how has it shaped our understanding of this elusive substance? The bullet cluster, officially known as 1EO 657-56, is located about 3.7 billion light-years from Earth. It consists of two galaxy clusters that have passed through one another in a high-speed collision. During this encounter, the galaxies within the clusters largely passed each other without much interaction, as galaxies are composed mostly of empty space. However, the gas clouds that make up the majority of the visible matter in each cluster collided, creating a dramatic shockwave that gives the bullet cluster its nickname. The most fascinating aspect of this collision lies in the separation between the visible matter, the hot gas clouds, and the gravitational mass of the clusters. Observations using X-ray telescopes, such as NASA's Chandra X-ray Observatory, reveal that the majority of the ordinary matter is concentrated in the hot gas, which emits intense X-ray radiation as a result of the collision. However, gravitational lensing studies, which map the total mass of the clusters, tell a different story. Gravitational lensing occurs when the light from background galaxies is bent by the gravitational field of a massive foreground object. By analyzing the distortions in this light, astronomers can map the distribution of mass in the bullet cluster. These lensing maps show that the majority of the mass is not in the hot gas but in two distinct regions corresponding to the locations of the galaxies. This mass distribution suggests the presence of dark matter, which did not interact with the gas clouds and passed through the collision unaffected. This separation of dark matter and ordinary matter is one of the clearest demonstrations that dark matter exists as a distinct entity. If the observed gravitational effects were due solely to the visible matter, the lensing maps would align with the locations of the hot gas clouds. Instead, the gravitational mass aligns with the galaxies, where dark matter is expected to dominate. The bullet cluster has also provided critical tests for alternative theories of gravity, such as modified Newtonian dynamics, MOND. These theories propose that the effects attributed to dark matter could instead result from changes in the laws of gravity at large scales. However, the bullet cluster poses a significant challenge to these theories. The separation between the hot gas and the gravitational mass cannot be easily explained by modified gravity alone, as the observed lensing effects require the presence of an unseen mass, dark matter. Beyond its implications for dark matter, the bullet cluster has deepened our understanding of galaxy cluster dynamics and cosmic evolution. The collision is one of the most energetic events observed in the universe, releasing energy equivalent to millions of supernovae. The shockwave created by the interaction of the gas clouds provides valuable insights into the physics of such collisions, including the behavior of hot plasma, the role of magnetic fields, and the impact on star formation within the clusters. Simulations of the bullet cluster have been instrumental in interpreting its features and understanding its significance. Using supercomputers, researchers can recreate the collision, modeling the behavior of both dark matter and ordinary matter. These simulations show how the dark matter halos of the two clusters pass through one another, while the gas clouds collide and slow down, creating the observed separation. They also help constrain the properties of dark matter, such as its self-interaction cross-section. Current simulations suggest that dark matter is largely collisionless, with minimal self-interactions. The bullet cluster is not the only example of such a collision, but it remains the most striking due to its clarity and the quality of the data available. Similar systems, such as the train wreck cluster, Able 520, and the musket ball cluster, exhibit comparable features but with varying degrees of complexity. Together, these systems provide a broader context for understanding the behavior of dark matter in different environments. As astronomers continue to study the Bullet Cluster, new questions emerge. What can the distribution of dark matter in this system tell us about its properties? Could subtle deviations from the predictions of cold dark matter models reveal new physics? And how do similar collisions contribute to the large-scale structure of the universe? Future observations and experiments will play a key role in answering these questions. Advanced telescopes, such as the James Webb Space Telescope and upcoming X-ray observatories like Athena, will provide deeper insights into the hot gas and star formation within such systems. Meanwhile, gravitational lensing studies with instruments like Euclid and the Vera C. Rubin Observatory will refine our maps of dark matter distribution, offering new opportunities to test theoretical models. The Bullet Cluster stands as a cosmic proving ground, a natural experiment that has helped solidify our understanding of dark matter. Its unique configuration and the wealth of data it provides make it a cornerstone of modern astrophysics. As we continue to study this remarkable system, it promises to reveal even more about the invisible forces that shape our universe. Anomalies in the data, the hints we can't ignore. In the quest to uncover the nature of dark matter, astronomers and physicists rely heavily on observational data, theoretical models, and simulations. Yet, amidst the growing body of evidence supporting the existence of dark matter, certain anomalies continue to challenge our understanding. These deviations, while puzzling, are invaluable. They could hold the keys to unlocking deeper truths about the universe and its hidden components. What are these anomalies, and what do they reveal about dark matter? One of the most intriguing anomalies arises from the behavior of dark matter in the centers of galaxies. According to simulations based on the cold dark matter (CDM) model, dark matter should form dense cusps at the cores of galaxies, with mass density increasing sharply toward the center. However, observations suggest otherwise. In many dwarf galaxies and low-surface brightness galaxies, the dark matter appears to form a core with a relatively uniform density. This discrepancy, known as the core cusp problem, challenges the standard CDM paradigm. To address the core cusp problem, researchers have proposed various solutions. Some suggest that interactions between dark matter particles, known as self-interacting dark matter (SIDM), could redistribute energy within halos, flattening the density profile. Others argue that feedback processes from supernova explosions or active galactic nuclei could push dark matter outward, creating the observed cores. However, neither explanation has been definitively proven, leaving the core cusp problem as an open question. Another anomaly comes from the distribution of satellite galaxies around larger galaxies like the Milky Way. Observations show that these satellite galaxies often align in thin, planar structures, rather than being randomly distributed as predicted by CDM simulations. This plane of satellites problem has been observed in both the Milky Way and Andromeda galaxies, and its persistence across multiple systems suggests it is not a mere coincidence. The cause of this alignment remains unclear. Some researchers propose that interactions within the cosmic web or tidal effect from large-scale structures could play a role, while others suggest the need for alternative dark matter models or modifications to gravity. The too big to fail problem is another well-known anomaly. Simulations of dark matter halos predict the existence of many massive subhalos within galaxies like the Milky Way. These subhalos should host bright satellite galaxies, but observations reveal far fewer than expected. Moreover, the most massive subhalos appear to be devoid of stars, contrary to predictions. This mismatch raises questions about the processes governing star formation in small halos and the nature of dark matter itself. Gravitational lensing studies have also uncovered unexpected features that challenge the CDM model. For example, observations of galaxy clusters reveal substructures in the dark matter distribution that are more massive and concentrated than predicted by simulations. These anomalies could hint at new properties of dark matter, such as self-interactions or a more complex particle spectrum. Alternatively, they might point to issues in the way simulations model baryonic processes or initial conditions. One particularly intriguing anomaly involves ultra-diffuse galaxies, UDGs, a class of faint galaxies with surprisingly low surface brightness. Some UDGs, like DF2 and DF4, appear to lack significant amounts of dark matter, contradicting the expectation that all galaxies are embedded in dark matter halos. If confirmed, these findings would challenge the notion that dark matter is the dominant driver of galaxy formation, suggesting a more nuanced relationship between visible and invisible matter. Beyond these specific cases, the behavior of dark matter on the largest scales of the universe presents its own puzzles. Observations of the cosmic microwave background, CMB, and the large-scale structure of the universe are generally consistent with the CDM model, but subtle deviations persist. For instance, measurements of the Hubble constant, which describes the rate of the universe's expansion, differ depending on the method used. This Hubble tension might hint at new physics, potentially involving dark matter's interaction with dark energy or modifications to our understanding of the early universe. Another large-scale anomaly involves the distribution of dark matter in cosmic voids. These vast, empty regions of space are surrounded by filaments of the cosmic web and contain few galaxies. Observations suggest that voids might have less dark matter than expected, challenging the assumption that dark matter is evenly distributed on large scales. Understanding these discrepancies could provide insights into the nature of dark matter and its interactions with other components of the universe. Some researchers have also explored the possibility that these anomalies could hint at entirely new paradigms. Alternative models, such as warm dark matter, WDM, propose that dark matter consists of lighter, faster-moving particles. These particles would form less dense halos and exhibit different clustering behaviors, potentially resolving some of the observed discrepancies. Other theories, like fuzzy dark matter, suggest that dark matter could be composed of ultralight particles with wave-like properties, creating interference patterns that shape its distribution. In the search for explanations, astronomers are turning to increasingly precise observations and simulations. Instruments like the Vera C. Rubin Observatory in Euclid will provide detailed maps of the universe's structure, helping to identify patterns that could clarify these anomalies. At the same time, laboratory experiments are probing the fundamental properties of dark matter particles, searching for signals that might explain their behavior. Despite the challenges they present, these anomalies are opportunities to advance our understanding of dark matter and the universe. They remind us that science is a process of discovery, where unexpected results often lead to breakthroughs. By investigating these discrepancies, researchers are not only testing the limits of current models, but also exploring the possibilities of entirely new physics. As we confront the hints we can't ignore, one question stands out. Could these anomalies be the key to unlocking the true nature of dark matter? The answers may redefine our understanding of the universe, revealing the hidden forces that govern its evolution and structure. Intergalactic mysteries, dark matter beyond our Milky Way. While the study of dark matter often begins within the confines of our own galaxy, its influence extends far beyond. The intergalactic realm, where galaxies interact and collide, holds crucial clues about the nature and behavior of dark matter. By exploring dark matter on these vast cosmic scales, scientists are uncovering new mysteries that challenge existing theories and illuminate the invisible scaffolding of the universe. What does dark matter look like beyond the Milky Way? And what can it teach us about the larger cosmos? The intergalactic environment is dominated by galaxy clusters, which are among the most massive structures in the universe. These clusters contain hundreds or even thousands of galaxies, along with hot gas that emits X-rays and an enormous amount of dark matter. Observations show that dark matter dominates the mass of galaxy clusters, providing the gravitational pull needed to hold them together. Without dark matter, the visible matter alone would be insufficient to counteract the energetic motions of galaxies within these clusters. Gravitational lensing has been a powerful tool for studying dark matter in galaxy clusters. By analyzing the distortions in the light from background galaxies, astronomers can map the distribution of dark matter within and around these clusters. The results reveal dense cores surrounded by extended halos of dark matter, which connect to the larger cosmic web. These observations confirm the presence of dark matter on intergalactic scales and provide insights into its density, distribution, and influence. One of the most fascinating aspects of dark matter in the intergalactic medium is its role in shaping the large-scale structure of the universe. The cosmic web, a vast network of filaments and voids, is largely dictated by the gravitational effects of dark matter. These filaments connect galaxy clusters and superclusters, creating highways for the flow of matter across the universe. The distribution of galaxies along these filaments reflects the underlying dark matter, making it a crucial component of cosmic evolution. The study of cosmic voids, immense regions of space that contain few galaxies, also offers unique insights into dark matter. These voids are not entirely empty. They contain sparse distributions of dark matter that influence their growth and shape. Observations of voids suggest that dark matter in these regions is less clumpy than in denser areas, providing clues about its properties and interactions. Interactions between galaxies and their surrounding dark matter halos play a critical role in galaxy evolution. For example, when a galaxy passes through the dense environment of a cluster, its dark matter halo can be stripped away by tidal forces, leaving the galaxy vulnerable to further disruption. This process, known as ram pressure stripping, affects the galaxy's gas content and star formation rate, highlighting the dynamic interplay between dark matter and baryonic matter. Galaxy mergers, common in the intergalactic environment, further illustrate the importance of dark matter. As discussed in the previous chapter, mergers involve the collision and eventual merging of dark matter halos, which shape the dynamics of the event. The behavior of dark matter during these interactions provides valuable constraints on its properties, such as its self-interaction cross-section. Observing these events on intergalactic scales helps refine models of dark matter and its role in cosmic evolution. Dwarf galaxies, often found orbiting larger galaxies or scattered throughout clusters, offer another window into dark matter's intergalactic role. These faint, low-mass galaxies are dominated by dark matter, making them ideal laboratories for studying its properties. Some dwarf galaxies show evidence of dark matter cores rather than cusps, contributing to the ongoing debate about the density profiles of dark matter halos. Others, such as ultra-diffuse galaxies, challenge assumptions about the relationship between dark matter and galaxy formation, as they appear to have disproportionately low or high amounts of dark matter. The intergalactic medium itself, composed of diffuse gas that spans the space between galaxies, is also influenced by dark matter. This gas, visible through its absorption lines in the spectra of distant quasars, traces the distribution of dark matter on large scales. By mapping the intergalactic medium, astronomers can infer the structure of the cosmic web and the role of dark matter in shaping it. Recent discoveries have deepened the mystery of dark matter in the intergalactic realm. Observations of diffuse light in clusters, known as intracluster light, ICL, suggest that dark matter may extend even farther than previously thought, encompassing regions of space far beyond the visible boundaries of galaxies and clusters. This diffuse halo of dark matter could play a critical role in connecting galaxies within clusters and influencing their interactions. The search for dark matter beyond our galaxy is also driving advancements in observational techniques. Future missions like the Euclid satellite and the Nancy Grace Roman Space Telescope aim to map dark matter on intergalactic scales with unprecedented precision. By studying weak gravitational lensing across vast areas of the sky, these instruments will provide a more detailed picture of the cosmic web and the distribution of dark matter. Despite the progress, many questions remain unanswered. Why does dark matter appear to cluster on certain scales, but not others? Could its distribution in the intergalactic medium reveal interactions beyond gravity? And how does its behavior influence the formation and evolution of the largest structures in the universe? Dark matter beyond the Milky Way is not just a distant mystery. It is a cornerstone of cosmic evolution. Its gravitational influence shapes galaxies, clusters, and the cosmic web, driving the dynamics of the intergalactic medium. By exploring these vast, unseen realms, scientists are piecing together the larger puzzle of dark matter, uncovering its role in the grand architecture of the universe. As we probe deeper into the intergalactic mysteries of dark matter, we edge closer to understanding the invisible forces that govern the cosmos. The answers lie not only in the spaces we can see, but also in the unseen realms that connect the stars, galaxies, and clusters into a unified cosmic whole. Tantalizing signals. The search for indirect evidence. While dark matter remains invisible to telescopes, scientists believe it might leave subtle, indirect traces of its existence. These tantalizing signals could emerge from the annihilation or decay of dark matter particles, producing detectable byproducts such as gamma rays, neutrinos, or charged particles. By searching for these faint clues, researchers hope to uncover the nature of dark matter and unlock one of the universe's greatest mysteries. But what are these signals, and how close are we to detecting them? One of the most promising approaches in the search for indirect evidence of dark matter involves gamma rays, the most energetic form of light. If dark matter particles can annihilate or decay, they could produce gamma rays detectable by instruments on Earth or in space. The center of the Milky Way is an ideal target for such searches, as it is thought to harbor a dense concentration of dark matter. Observations by the Fermi Gamma Ray Space Telescope have revealed an excess of gamma rays emanating from this region, sparking intense debate about their origin. The galactic center gamma ray excess, as it is known, could be a signal of dark matter annihilation, but it might also result from more conventional astrophysical sources, such as millisecond pulsars or other high-energy processes. Disentangling these possibilities requires sophisticated modeling of the gamma ray background and further observations, but the excess remains one of the most intriguing hints of dark matter's presence. Dwarf spheroidal galaxies, small satellite galaxies of the Milky Way, provide another key target for gamma ray searches. These galaxies are rich in dark matter, but contain little ordinary matter, reducing the likelihood of competing gamma ray sources. Observations of dwarf galaxies by Fermi and other instruments have not yet yielded definitive signals of dark matter annihilation, but they continue to provide valuable constraints on dark matter models. Neutrinos, nearly massless particles that interact weakly with matter, offer another potential pathway to detect dark matter. If dark matter particles decay or annihilate, they could produce high-energy neutrinos detectable by observatories like IceCube, a neutrino telescope buried deep in the Antarctic ice. IceCube has observed astrophysical neutrinos from distant galaxies, but no definitive signals from dark matter have yet been identified. However, the unique properties of neutrinos make them a promising avenue for future research. Antimatter, particularly positrons and antiprotons, is another potential byproduct of dark matter interactions. Experiments like the Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, and the Pamela satellite have detected excesses of positrons in cosmic rays. These positron excesses could be a signature of dark matter annihilation, but they might also arise from astrophysical sources such as pulsars or supernova remnants. Understanding these excesses requires careful analysis and improved models of cosmic ray propagation. X-rays provide yet another window into dark matter's potential decay products. Certain dark matter candidates, such as sterile neutrinos, could decay into X-rays over cosmic timescales. Observations of galaxy clusters and the Milky Way's halo have revealed unexplained X-ray emissions at specific energies, leading some researchers to propose a connection to dark matter. The 3.5 keV line, a spectral feature observed in several independent datasets, remains a candidate signal, though its interpretation is still debated. The search for indirect evidence of dark matter extends beyond our galaxy to the largest structures in the universe. Clusters of galaxies, which harbor vast amounts of dark matter, are prime targets for gamma-ray and X-ray observations. By studying these clusters, scientists aim to detect faint signals that could reveal the properties of dark matter particles. Ground-based telescopes also play a crucial role in this effort. Observatories like the Cherenkov Telescope Array, CTA, and HESS detect gamma rays through the flashes of light, or Cherenkov radiation, produced when these high-energy photons interact with Earth's atmosphere. These instruments complement space-based observatories, providing higher sensitivity to gamma rays from potential dark matter sources. Despite the lack of a definitive detection, indirect searches for dark matter have significantly advanced our understanding of its properties. Each null result narrows the range of possible characteristics, such as the mass of dark matter particles and the strength of their interactions. These constraints inform theoretical models and guide the design of future experiments. One of the challenges in interpreting potential dark matter signals is distinguishing them from astrophysical background. Pulsars, supernova remnants, and active galactic nuclei can all produce gamma rays, neutrinos, and other high-energy emissions. To address this, researchers use sophisticated statistical techniques and simulations to separate potential dark matter signals from background noise. The search for indirect evidence is not just about detecting a single signal. It is about building a consistent picture that links different observations. For example, a gamma ray excess observed in the galactic center might be correlated with a neutrino signal from galaxy clusters or an antimatter excess in cosmic rays. Such connections would strengthen the case for dark matter and provide critical clues about its nature. As technology advances, the sensitivity of indirect detection experiments continues to improve. Next-generation instruments like the CTA and planned space missions will probe deeper into the high-energy universe, expanding the search for dark matter signals. These efforts are complemented by laboratory experiments and direct detection searches, creating a multi-pronged approach to solving the dark matter puzzle. Indirect searches are a testament to the ingenuity of science, transforming subtle cosmic clues into tools for discovery. While the evidence remains tantalizingly out of reach, each step forward brings us closer to revealing the nature of dark matter and its role in the universe. As the search intensifies, one question lingers. Could the signals we observe today be the whispers of dark matter, waiting to be heard? The answer may reshape our understanding of the cosmos and the forces that govern its evolution. Cosmic archaeology: what dark matter tells us about the past. Dark matter is not just a force shaping the present universe. It is a silent witness to its history, holding clues to the cosmos's evolution from the Big Bang to the formation of galaxies. By studying the distribution and behavior of dark matter, scientists are piecing together a timeline of cosmic events, unveiling how the universe evolved over billions of years. But what stories does dark matter tell about the past? And how does its presence help us uncover the origins of the universe? To understand dark matter's role in cosmic history, we must start at the beginning. In the moments after the Big Bang, the universe was a hot, dense plasma of particles and radiation. Dark matter, which interacts only through gravity and possibly weak forces, began clumping together almost immediately as the universe expanded and cooled. Unlike ordinary matter, which was coupled to radiation through electromagnetic forces, dark matter was free to form dense regions, laying the groundwork for the large-scale structure of the cosmos. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, provides a snapshot of the universe approximately 380,000 years after its birth. The tiny fluctuations in the CMB's temperature and polarization reflect variations in the density of both dark matter and ordinary matter. These fluctuations served as seeds for the formation of galaxies and clusters, with dark matter providing the gravitational scaffolding needed for ordinary matter to collapse and form stars. Without dark matter, these density variations would have been too small to overcome the smoothing effects of radiation, and the universe would lack the structure we see today. As the universe evolved, dark matter continued to shape its development. By a few hundred million years after the Big Bang, the first dark matter halos had formed, providing the environments where gas could cool and condense into the earliest stars. These stars, known as population 3 stars, were massive and short-lived, producing heavy elements and creating the first feedback effects on their surroundings. The interplay between these stars and their dark matter halos influenced the formation of subsequent generations of stars and galaxies. One of the most remarkable aspects of dark matter is its role in the cosmic web. This vast network of filaments, nodes, and voids traces the distribution of dark matter across the universe, shaping where galaxies and clusters form. By mapping the cosmic web, astronomers can reconstruct the history of matter's distribution and the processes that drove its evolution. Observations of the large-scale structure, combined with simulations, allow scientists to trace the growth of dark matter halos over billions of years. Galaxy clusters, the largest gravitationally bound structures in the universe, are another key to understanding cosmic history. These clusters formed from the merging of smaller structures, a process driven by the gravitational pull of dark matter. The study of clusters provides insights into the timeline of structure formation and the distribution of dark matter on the largest scales. Gravitational lensing, which reveals the distribution of mass in clusters, serves as a tool for probing these ancient mergers and the role of dark matter in shaping them. On smaller scales, dwarf galaxies offer a glimpse into the early universe. These faint, low-mass galaxies are thought to be some of the oldest objects in the cosmos, with their dark matter halos preserving a record of their formation history. By studying the motions of stars within dwarf galaxies, astronomers can infer the properties of their dark matter halos and test theories about the early stages of galaxy formation. Dark matter also plays a role in understanding reionization, a key phase in cosmic history when the first stars and galaxies ionized the neutral hydrogen that filled the universe. The distribution of dark matter influenced where and when this reionization occurred, as dense regions formed earlier and produced more ionizing radiation. By studying the effects of reionization on the intergalactic medium, researchers can gain insights into the interplay between dark matter and the first luminous objects. Even the most recent stages of cosmic history are shaped by dark matter. The growth of supermassive black holes at the centers of galaxies, the evolution of galaxy clusters, and the interactions between galaxies all depend on the underlying distribution of dark matter. For example, dark matter halos provide the gravitational wells that guide the flow of gas and stars during galaxy mergers, fueling the growth of black holes and triggering starbursts. Cosmic archaeology, the process of reconstructing the universe's history through observation and simulation, relies heavily on dark matter as a tracer of past events. Advanced simulations, such as the Illustris and Eagle projects, allow scientists to model the formation and evolution of galaxies within a dark matter framework. These simulations incorporate the effects of baryonic processes, such as star formation and feedback, providing a detailed picture of how the visible and invisible components of the universe interact. Observational techniques are also evolving to probe the history of dark matter more directly. Instruments like the James Webb Space Telescope and the Vera C. Rubin Observatory will enable deeper studies of the earliest galaxies, revealing how dark matter influenced their formation. Gravitational lensing, meanwhile, continues to provide critical data on the distribution of dark matter in both nearby and distant structures. As we delve deeper into the past, one of the most profound questions remains: what is the ultimate origin of dark matter? Some theories suggest that dark matter particles were produced in the first fractions of a second after the Big Bang, through processes related to inflation or high-energy physics beyond the Standard Model. Others propose that dark matter could have arisen from interactions in hidden dimensions or alternative frameworks for understanding gravity. By studying dark matter's role in cosmic history, scientists are not only uncovering the story of the universe, but also testing the limits of current theories. Each observation and simulation adds a new chapter to this story, bringing us closer to understanding the forces that have shaped the cosmos for billions of years. Dark matter is more than a mystery. It is a key to unlocking the past. Through its gravitational influence, it has preserved a record of the universe's evolution, guiding the formation of galaxies, stars, and planets. As we continue to explore this hidden dimension of the cosmos, we uncover not only the origins of structure, but also the profound interconnectedness of all things in the universe. A universe without dark matter, imagining the unthinkable. What would the cosmos look like if dark matter did not exist? This thought experiment forces us to reconsider the fundamental forces that shape our universe, offering insights into why dark matter is so essential. Without dark matter's gravitational influence, galaxies, stars, and the very fabric of the universe as we know it would be radically different. But how different? And what does this reveal about the role of dark matter in the grand scheme of the cosmos? To answer these questions, we must revisit the early universe. Following the Big Bang, the cosmos was a hot, dense plasma of particles and radiation, with slight density fluctuations seeded by quantum mechanics during inflation. Dark matter, because it does not interact with radiation, began to clump almost immediately, forming the gravitational wells that ordinary matter would later fall into. Without dark matter, these wells would not exist, and ordinary matter, interacting with radiation, would struggle to form structures. In a universe devoid of dark matter, the first major consequence would be the absence of the cosmic web. Dark matter's gravitational pull shapes the large-scale structure of the universe, creating the vast network of filaments, voids, and nodes where galaxies and clusters reside. Without dark matter, this scaffolding would collapse, leaving a universe where matter is far more evenly distributed. Galaxies, if they formed at all, would be scattered randomly rather than aligned along filamentary structures. Galaxy formation itself would face significant challenges. In our universe, dark matter halos serve as the gravitational cradles for galaxies, providing the mass necessary to bind stars, gas, and other components together. Without these halos, ordinary matter would lack the gravitational cohesion needed to cool and condense into galaxies. The result would be a universe with far fewer galaxies, and those that did form would likely be small, irregular, and short-lived. Even if galaxies managed to form, their internal dynamics would be drastically different. Observations of galaxy rotation curves show that stars in the outer regions of spiral galaxies orbit at nearly the same speed as those closer to the center, a behavior explained by the presence of an extended dark matter halo. In a universe without dark matter, these rotation curves would decline sharply, as the gravitational pull of visible matter alone would not be sufficient to hold outer stars in their orbits. Over time, galaxies would become unstable, with stars dispersing into intergalactic space. Star formation, too, would be profoundly affected. Dark matter halos draw in gas, creating the dense environments needed for stars to form. Without dark matter, the supply of gas would be less concentrated, leading to a slower rate of star formation. The lack of gravitational support from dark matter halos would also make it harder for galaxies to retain their gas, further suppressing the creation of new stars. On larger scales, the absence of dark matter would disrupt the formation of galaxy clusters. These massive structures, which contain hundreds or thousands of galaxies, rely on the gravitational influence of dark matter to stay bound. Without dark matter, clusters would be far less common and much less massive, fundamentally altering the cosmic landscape. The effects of a universe without dark matter extend to the intergalactic medium and the cosmic microwave background, CMB. The distribution of dark matter influences the behavior of intergalactic gas, shaping the Lyman alpha forest, a pattern of absorption lines in the spectra of distant quasars. Without dark matter, this pattern would be far less pronounced, offering a much weaker probe of cosmic evolution. The CMB itself would also bear the marks of a dark matter-free universe. The small fluctuations in the CMB's temperature and polarization reflect the influence of dark matter on the early universe's density variations. Without dark matter, these fluctuations would be significantly smaller, leading to a universe with weaker gravitational seeds for structure formation. The geometry and expansion history of the universe, encoded in the CMB, would also be dramatically different. Interestingly, the absence of dark matter might also affect the behavior of black holes. Supermassive black holes at the centers of galaxies grow by accreting matter and merging with other black holes, processes influenced by the distribution of dark matter. Without dark matter halos to funnel gas and stars toward the galactic center, the growth of supermassive black holes would be severely hindered. This, in turn, would impact the activity of quasars and the role of black holes in galaxy evolution. The implications of a dark matter-free universe extend to the ultimate fate of the cosmos. Dark matter plays a critical role in counteracting the effects of dark energy, the mysterious force driving the accelerated expansion of the universe. Without dark matter, dark energy would dominate even more strongly, leading to a universe that expands faster and fragments into isolated, empty regions more quickly. This thought experiment underscores the profound impact of dark matter on every aspect of the cosmos. From the formation of the first galaxies to the large-scale structure of the universe, dark matter provides the gravitational framework that makes the universe as we know it possible. Without it, the cosmos would be a very different place, simpler, less structured, and far less hospitable to the formation of stars, planets, and life. Imagining a universe without dark matter also highlights the interconnectedness of cosmic phenomena. The absence of dark matter would not just affect individual galaxies or clusters. It would reshape the entire evolutionary history of the universe. This interconnectedness reinforces the importance of dark matter in understanding the cosmos, even as its true nature remains one of the greatest mysteries in science. As we consider the unthinkable, a universe without dark matter, we gain a deeper appreciation for the forces that shape our reality. Dark matter, though invisible and elusive, is a cornerstone of the cosmos, guiding its formation and evolution across billions of years. Its presence reminds us that the universe is far richer and more complex than what we can see, a testament to the unseen forces that govern existence. Theories under fire, alternative explanations. The mysterious nature of dark matter has sparked decades of debate and inspired numerous alternative theories. While the evidence for dark matter is compelling, some researchers have sought to explain the universe's gravitational behavior without invoking an unseen substance. These alternative explanations challenge the conventional paradigm, offering different perspectives on how gravity and matter behave on cosmic scales. But how do these theories hold up under scrutiny, and what can they teach us about the universe? One of the most prominent alternatives to dark matter is modified Newtonian dynamics, or MOND. Proposed in the 1980s by Israeli physicist Mordechai Milgrom, MOND suggests that the laws of gravity change at very low accelerations, such as those found on the outskirts of galaxies. According to MOND, the flat rotation curves of spiral galaxies, where stars at the edges move faster than expected, can be explained without dark matter by modifying Newton's laws. MOND has been successful in describing certain galactic phenomena, particularly the rotation curves of individual galaxies. However, it struggles to account for larger-scale structures like galaxy clusters and the cosmic web, where dark matter's influence is most evident. Moreover, MOND is fundamentally incompatible with general relativity, making it difficult to integrate into the broader framework of modern physics. Despite these limitations, MOND remains an intriguing idea, prompting researchers to explore hybrid models that combine elements of MOND with dark matter. Building on the principles of MOND, some researchers have developed theories of modified gravity that go beyond Newtonian mechanics. Tensor vector scalar gravity, TeVS, for example, is a relativistic extension of MOND that incorporates additional fields to modify gravity on cosmic scales. While TeVS offers a more complete framework, it still faces challenges in explaining phenomena like the bullet cluster, where the separation between visible matter and gravitational mass strongly supports the existence of dark matter. Another alternative is the concept of emergent gravity, proposed by Dutch theoretical physicist Erik Verland. Emergent gravity suggests that gravity is not a fundamental force, but an emergent phenomenon arising from the thermodynamic properties of space-time. In this framework, the effects attributed to dark matter could result from changes in the entropy of the universe's underlying structure. While this idea is highly speculative, it has generated significant interest as a potential way to reconcile gravity with quantum mechanics. Some researchers have proposed that dark matter might not be a particle at all, but instead a modification of space-time itself. In this view, phenomena like galaxy rotation curves and gravitational lensing could be explained by additional geometric structures in space-time, such as extra dimensions or topological defects. These theories often draw inspiration from string theory and other approaches to quantum gravity, offering a radically different perspective on the universe's hidden forces. Despite their appeal, these alternative theories face significant hurdles. One of the most compelling pieces of evidence for dark matter is the behavior of galaxy clusters like the bullet cluster, where gravitational lensing reveals a clear separation between visible matter and the total gravitational mass. This separation is difficult to reconcile with modified gravity theories, which generally predict that gravitational effect should align with visible matter. Another challenge comes from the cosmic microwave background, CMB. The tiny fluctuations in the CMB's temperature and polarization reflect the influence of dark matter during the universe's early stages. Alternative theories must replicate these effects while also explaining the growth of large-scale structures, a task that has proven exceedingly difficult. Hybrid models, which combine elements of dark matter and modified gravity, offer a potential way forward. These models suggest that dark matter might exist, but behave differently than previously thought, with properties that vary across different scales or environments. For example, self-interacting dark matter, SIDM, introduces the idea that dark matter particles could interact with one another, affecting their distribution and dynamics in ways that mimic modified gravity on small scales. The search for alternatives has also led to new experimental and observational efforts. By studying phenomena like gravitational waves, the expansion of the universe, and the behavior of dark matter on different scales, scientists are testing the limits of both conventional and alternative theories. These efforts are complemented by laboratory experiments, searching for deviations from standard physics that might hint at new gravitational laws or exotic particles. Despite their challenges, alternative theories play a vital role in the scientific process. They encourage researchers to question assumptions, test the boundaries of existing models, and explore new ideas. In some cases, these theories have led to unexpected discoveries, such as the realization that dark matter might have more complex interactions than previously believed. Ultimately, the debate over dark matter and its alternatives reflects the evolving nature of science. As new data emerges and technologies advance, our understanding of the universe continues to deepen, revealing complexities that challenge our most fundamental beliefs. Whether dark matter exists as a particle, a modification of gravity, or something entirely unexpected, the search for answers drives us to explore the unknown. As we confront the limitations of our current theories, one question remains: could the true nature of dark matter lie beyond the boundaries of what we can currently imagine? The answers may redefine not only our understanding of the cosmos, but also the very nature of reality itself. Enter the void, dark matter in empty space. Dark matter is often associated with galaxies and galaxy clusters, where its gravitational influence is most obvious. However, its presence extends far beyond these dense regions, permeating the vast cosmic voids, immense, seemingly empty regions of space that make up much of the universe's volume. These voids are the darkest and loneliest places in the cosmos, yet they hold critical clues about the behavior and distribution of dark matter. What role does dark matter play in these empty spaces, and what can we learn from studying its effects in the void? Cosmic voids are enormous regions spanning tens to hundreds of millions of light-years, containing few galaxies compared to the denser regions of the cosmic web. While they are less populated, voids are not completely empty. They contain sparse distributions of dark matter, gas, and occasional faint galaxies. These underdense regions are bounded by the filaments and nodes of the cosmic web, where dark matter and ordinary matter are concentrated. The formation of voids is a natural consequence of the universe's large-scale structure. After the Big Bang, regions with slightly higher densities of dark matter began to collapse under gravity, forming the seeds of galaxies and clusters. Meanwhile, underdense regions expanded as matter flowed outwards, leaving behind voids. Over billions of years, these voids grew larger, shaped by the gravitational pull of the surrounding dark matter and baryonic structures. Dark matter's role in voids is subtle but significant. Unlike in dense regions, where dark matter clumps into halos, the distribution of dark matter in voids is much smoother. This difference provides an opportunity to study dark matter's properties in environments where its interactions with ordinary matter are minimal. By analyzing the behavior of dark matter in voids, researchers can test theories about its nature, such as whether it is truly collisionless or has self-interactions. One of the most intriguing aspects of dark matter in voids is its influence on the motion of galaxies at the edges of these empty regions. Galaxies and clusters surrounding voids are drawn together by the gravitational pull of dark matter in the filaments, creating distinct patterns of motion. By measuring these motions, astronomers can infer the distribution of dark matter around voids and test predictions from cosmological models. Voids also provide a unique perspective on the interplay between dark matter and dark energy. In these underdense regions, the effects of dark energy, responsible for the accelerated expansion of the universe, are amplified. Studying voids allows scientists to isolate and measure these effects, offering insights into how dark energy interacts with the underlying dark matter framework. For example, the shapes and sizes of voids are sensitive to the balance between dark matter and dark energy, making them a valuable tool for probing the universe's expansion history. Observationally, voids are challenging to study because of their low density and faint features. However, Advances in large-scale surveys have made it possible to map voids in detail. Projects like the Sloan Digital Sky Survey, SDSS, and upcoming missions like Euclid and the Vera C. Rubin Observatory are providing high-resolution maps of the cosmic web, including the distribution of voids. These maps reveal not only the locations of voids but also the surrounding structures, allowing researchers to analyze the relationship between voids and the larger cosmic environment. Gravitational lensing, a technique traditionally used to study dense regions, is also being applied to voids. While the lensing signals from voids are weaker, they provide critical information about the distribution of dark matter in these regions. By combining lensing data with simulations, scientists can reconstruct the density profiles of voids and explore how dark matter behaves in these vast, underdense areas. Voids also offer opportunities to test alternative theories of gravity and dark matter. In modified gravity models, for example, the behavior of dark matter and baryonic matter in voids could differ from standard predictions. By comparing observations of voids with simulations based on alternative theories, researchers can identify potential deviations that might hint at new physics. Despite their sparse nature, voids are not devoid of activity. Faint galaxies, known as void galaxies, inhabit these regions, often displaying unique properties. These galaxies are typically isolated, with lower star formation rates and simpler morphologies than their counterparts in denser environments. Their existence challenges traditional models of galaxy formation, suggesting that even in the emptiest regions, dark matter plays a critical role in shaping cosmic structures. Voids are also sensitive to the properties of dark matter on the smallest scales. For instance, if dark matter consists of warm particles or has significant self-interactions, it could suppress the formation of small-scale structures within voids. Observations of the smallest galaxies and their distribution in voids provide constraints on these properties, helping to refine models of dark matter. In addition to their scientific value, voids offer a striking reminder of the vastness and complexity of the universe. These empty spaces, though seemingly insignificant, are critical to the overall balance of the cosmos. They highlight the interplay between matter and gravity on the largest scales, showcasing the interconnectedness of all cosmic phenomena. As technology advances and observations become more precise, the study of dark matter and voids is poised to uncover new insights into the universe's hidden architecture. By exploring the darkest corners of the cosmos, we move closer to understanding the forces that shape reality itself. In the emptiness of the void, dark matter weaves its subtle threads, connecting the visible and invisible in ways we are only beginning to comprehend. As we continue to explore these enigmatic regions, one question remains. Could the secrets of dark matter lie not in what is present, but in the vast expanses where almost nothing exists? The role of supercomputers, pioneering dark matter research. Understanding dark matter, the invisible force that governs much of the universe's structure, requires tools as vast and powerful as the cosmos itself. Enter the supercomputer, an extraordinary blend of computational might and precision. These machines are at the forefront of dark matter research, enabling scientists to simulate the universe, test theories, and predict the behavior of the unseen. But how do supercomputers advance our understanding of dark matter, and what discoveries have they made possible? Supercomputers are essential for studying dark matter because the phenomena involved span vast scales, from the tiniest quantum interactions to the largest structures in the universe. To capture this complexity, researchers rely on numerical simulations that model the behavior of dark matter under the influence of gravity, along with its interactions with ordinary matter. These simulations generate immense datasets that would be impossible to process without supercomputing power. One of the most significant contributions of supercomputers is their ability to simulate the universe's evolution. Starting with conditions derived from the cosmic microwave background, CMB, simulations trace the development of the universe over billions of years. These models reveal how dark matter clumped into halos, creating the scaffolding for galaxies and clusters. They also show how the interplay between dark matter, ordinary matter, and dark energy shaped the cosmic web, the intricate network of filaments, nodes, and voids that define the universe's large-scale structure. Pioneering simulations like the Millennium Simulation, Illustris, and Eagle have transformed our understanding of dark matter. These projects use billions of particles to represent dark matter, tracking their movements and interactions over time. The resulting maps of the universe provide strikingly accurate representations of the observed distribution of galaxies and clusters, validating the cold, dark matter (CDM) model. They also reveal details about the density profiles of dark matter halos, the behavior of subhalos, and the formation of structures on different scales. Beyond large-scale structures, supercomputers are crucial for exploring the properties of dark matter particles themselves. By modeling how different types of dark matter behave, such as cold, warm, or self-interacting dark matter, simulations can predict observable differences in galaxy formation and distribution. These predictions guide observational efforts, helping scientists identify potential signatures of different dark matter models. For example, simulations have highlighted the core-cusp problem, a discrepancy between the predicted and observed density profiles of dark matter in galaxy centers. While the CDM model predicts steep cusps, observations often show flatter cores. Supercomputers allow researchers to test various explanations, from feedback processes driven by supernovae to alternative dark matter models like self-interacting dark matter. By adjusting parameters and comparing results with observations, simulations provide valuable insights into the underlying physics. Supercomputers also play a vital role in studying dark matter's role in galaxy mergers, cluster collisions, and cosmic voids. These events involve complex gravitational interactions that require detailed modeling to understand. For instance, simulations of the Bullet cluster have revealed how dark matter halos behave during high-speed collisions, offering critical evidence for the existence of dark matter as a distinct entity. Another area where supercomputers excel is in gravitational lensing. By simulating how light bends around massive structures, researchers can create virtual lensing maps that mimic real observations. Comparing these maps with data from telescopes allows scientists to infer the distribution of dark matter and test theories about its behavior. The computational demands of dark matter research have driven innovations in hardware and algorithms. Modern supercomputers like Summit, located at Oak Ridge National Laboratory, and Fugaku in Japan are capable of performing quadrillions of calculations per second. These machines use advanced architectures, including GPUs, graphics processing units, to handle the massive parallel computations required for simulations. New algorithms, such as adaptive mesh refinement, allow simulations to focus computational resources on the most important regions, improving efficiency and accuracy. Machine learning and artificial intelligence (AI) are also transforming how supercomputers are used in dark matter research. AI algorithms can analyze the vast datasets generated by simulations, identifying patterns and anomalies that might otherwise go unnoticed. For example, machine learning has been used to predict the properties of dark matter halos based on their environments, providing new ways to interpret observational data. AI is also speeding up simulations, enabling researchers to explore a wider range of parameters in less time. As observational capabilities improve, supercomputers are increasingly being used to bridge the gap between theory and data. Next-generation telescopes like the Vera C. Rubin Observatory, Euclid, and the James Webb Space Telescope will produce unprecedented amounts of data on the universe's structure and evolution. Supercomputers will play a critical role in analyzing this data, comparing it with simulations, and refining our understanding of dark matter. Despite their power, supercomputers are not without limitations. Simulations are only as good as the assumptions they are based on, and uncertainties in the initial conditions or physical processes can affect the results. For example, modeling the effects of baryonic processes like star formation and feedback remains challenging, as these phenomena involve complex physics that occur on smaller scales than many simulations can resolve. Addressing these challenges requires a combination of computational advances, improved observational data, and interdisciplinary collaboration. The future of supercomputing in dark matter research is bright. Emerging technologies like quantum computing promise to revolutionize simulations, enabling researchers to tackle problems that are currently intractable. Meanwhile, the integration of multi-messenger astronomy, combining data from electromagnetic radiation, gravitational waves, and neutrinos, will provide new opportunities to test dark matter theories across different regimes. Supercomputers are more than just tools. They are virtual laboratories where scientists can explore the hidden dimensions of the universe. By simulating the behavior of dark matter and its interactions with other cosmic components, these machines allow us to test theories, predict observations, and uncover the fundamental forces shaping reality. As we continue to push the boundaries of computation, one question remains. Could the next breakthrough in supercomputing finally reveal the true nature of dark matter? The answer lies in the partnership between human ingenuity and technological power, as we strive to illuminate the unseen forces that govern the cosmos. The future of dark matter research, unveiling the invisible. Dark matter research stands at the threshold of a new era. As technologies advance and theories evolve, the quest to uncover the nature of this elusive substance is accelerating. From cutting-edge experiments to revolutionary telescopes and innovative theoretical frameworks, the future of dark matter research promises to reshape our understanding of the universe. What breakthroughs lie ahead, and how will they transform our grasp of this cosmic mystery? One of the most exciting frontiers in dark matter research is direct detection. Experiments like the LUX Zeppelin, LZ, detector, and the upcoming Darwin Project aim to identify dark matter particles by capturing their rare interactions with ordinary matter. These detectors are housed deep underground to shield them from cosmic rays and background radiation, allowing them to search for faint signals such as nuclear recoils or scintillation events. With ever-increasing sensitivity, these experiments could finally reveal the properties of weakly interacting massive particles, WIMPs, or other dark matter candidates. Another avenue for progress is indirect detection, which seeks to observe the byproducts of dark matter interactions, such as gamma rays, neutrinos, or antimatter. Instruments like the Cherenkov Telescope Array, CTA, and next-generation neutrino observatories will provide unprecedented capabilities for detecting these signals. By targeting regions of high dark matter density, such as the galactic center or dwarf spheroidal galaxies, these efforts may uncover subtle clues about dark matter's behavior and interactions. Particle accelerators like the Large Hadron Collider, LHC, are also playing a critical role in the search for dark matter. By smashing protons together at near-light speeds, the LHC probes the fundamental forces of nature, searching for new particles that could constitute dark matter. Future upgrades to the LHC and planned facilities like the International Linear Collider and the Future Circular Collider will push the boundaries of energy and precision, opening new windows into the dark sector. Astrophysical and cosmological observations will be equally crucial in the coming years. The Vera C. Rubin Observatory, Euclid, and the Nancy Grace Roman Space Telescope will provide detailed maps of the universe's large-scale structure, revealing how dark matter shapes galaxies, clusters, and the cosmic web. These surveys will also refine measurements of dark energy, allowing scientists to explore the interplay between these two mysterious components of the universe. Gravitational wave observatories such as LIGO, Virgo, and the upcoming LISA mission are poised to revolutionize dark matter research by providing new ways to probe its effects. For example, dark matter halos around black holes could influence the gravitational waves emitted during mergers, offering indirect evidence of dark matter's distribution and properties. These observations could also test exotic theories, such as the existence of primordial black holes as a form of dark matter. Theoretical advancements will guide and complement these experimental efforts. Researchers are exploring a wide range of dark matter models, from axions and sterile neutrinos to self-interacting and fuzzy dark matter. These models offer diverse predictions, from unique particle interactions to wave-like behaviors on large scales. Testing these predictions requires a collaborative effort across disciplines, combining particle physics, astrophysics, and cosmology. Emerging technologies like quantum computing and machine learning are set to play transformative roles in dark matter research. Quantum computers could simulate the behavior of dark matter under extreme conditions, exploring scenarios that are computationally prohibitive for classical systems. Machine learning algorithms, meanwhile, are being used to analyze vast datasets from simulations and observations, identifying patterns and anomalies that might hint at dark matter's presence. Interdisciplinary approaches are also gaining traction, as scientists explore connections between dark matter and other unresolved mysteries. For example, some theories suggest links between dark matter and dark energy, while others propose that dark matter could interact with hidden dimensions or new forces of nature. These ideas challenge conventional frameworks, encouraging researchers to think beyond established paradigms. As we look to the future, one of the most profound questions remains: what will the discovery of dark matter mean for humanity? Understanding its nature could transform our understanding of the universe, shedding light on its origins, evolution, and ultimate fate. It could also inspire new technologies, as breakthroughs in fundamental physics often lead to unforeseen applications. The search for dark matter is more than a scientific endeavor. It is a testament to humanity's curiosity and ingenuity. It reminds us that the universe is far richer and more mysterious than we can imagine, and that the pursuit of knowledge is a journey with no final destination. In the decades to come, the convergence of technology, theory, and observation will bring us closer to solving the mystery of dark matter. Whether through the discovery of a particle, the observation of an indirect signal, or the refinement of a revolutionary theory, the next chapters in this story promise to be as transformative as the cosmos itself. The future of dark matter research is bright, even if the substance itself remains unseen. As we continue to push the boundaries of science, one thing is certain: the search for dark matter will redefine our place in the universe, revealing the hidden forces that shape reality. Dark matter and the origins of life, a surprising connection. While dark matter's influence is most evident on cosmic scales, its role in shaping the universe may have far-reaching implications for the very origins of life. From the formation of galaxies and stars to the conditions that made Earth habitable, dark matter's unseen presence has indirectly influenced the environments where life could emerge. Could this elusive substance be a silent architect of the cosmos's most profound phenomena? The connection between dark matter and life begins with its role in galaxy formation. Shortly after the Big Bang, dark matter clumped into halos, providing the gravitational pull needed to gather gas and form the first galaxies. These galaxies became the cradles of star formation, where elements like carbon, oxygen, and nitrogen were forged in stellar cores. Without dark matter's influence, the universe would lack the structures necessary to create these essential elements, leaving it barren and inhospitable. Dark matter's contribution to the stability of galaxies is another key factor. By providing an extended halo of gravitational support, dark matter ensures that galaxies remain intact over billions of years, despite the dynamic forces at play within them. This stability is crucial for the formation of planetary systems, as it allows stars to form and evolve without being disrupted by gravitational interactions with neighboring galaxies. The distribution of dark matter in the universe also influences the conditions for life. Dark matter shapes the large-scale structure of the cosmos, creating the cosmic web of filaments and voids. This web determines where galaxies form and cluster, affecting the distribution of stars, planets, and the chemical elements needed for life. The relative isolation of galaxies in cosmic voids, for example, could lead to quieter environments with fewer disruptive interactions, potentially favoring the development of complex life. On smaller scales, dark matter may have played a role in the formation of our own solar system. Some theories suggest that dark matter's gravitational influence helped shape the protosolar nebula, guiding the distribution of gas and dust that eventually formed the sun and planets. While this idea remains speculative, it highlights the potential for dark matter to affect the environments where planetary systems emerge. Even in the present day, dark matter may continue to influence life in subtle ways. For example, some researchers have proposed that dark matter could interact with biological systems through weak forces or gravitational effects. While no evidence for such interactions has been found, the idea underscores the possibility that dark matter's influence extends beyond astrophysics. The search for life beyond Earth is also intertwined with the study of dark matter. Exoplanets orbiting stars and other galaxies may owe their existence to the same processes shaped by dark matter in our own galaxy. By understanding how dark matter influences the formation and evolution of galaxies, scientists can better assess the potential for habitable worlds elsewhere in the cosmos. One of the most intriguing questions is whether dark matter could play a direct role in the emergence of life. Some speculative theories propose that dark matter particles might have unique properties that interact with the physical or chemical processes underlying life. For example, if dark matter interacts weakly with ordinary matter, it could subtly influence the behavior of molecules or the conditions within planetary interiors. While these ideas remain speculative, they highlight the profound interconnectedness of the universe. Dark matter, though invisible and enigmatic, is a fundamental part of the cosmic story, shaping the environments where life can exist. Its presence reminds us that the forces that govern the universe operate on scales both vast and intimate, connecting galaxies and stars to the smallest forms of life. The relationship between dark matter and life also raises philosophical questions about our place in the universe. If dark matter has indirectly enabled the conditions for life, it underscores the delicate balance of forces that make existence possible. This perspective invites us to consider how the universe's hidden components contribute to its beauty and complexity. As we continue to study dark matter, its connection to the origins of life may become clearer. Future missions and experiments, from space telescopes to particle detectors, will deepen our understanding of dark matter's role in shaping the cosmos. These efforts are not just about solving a scientific mystery. They are about uncovering the story of how the universe gave rise to life. Dark matter, though unseen, is an integral part of this story. By exploring its influence, we gain a deeper appreciation for the forces that have shaped the universe and our place within it. The search for dark matter is not just a quest for knowledge. It is a journey to understand the profound connections that bind the cosmos together. A multiverse of shadows. Could dark matter reveal hidden realms? As scientists delve deeper into the mysteries of dark matter, some theories point to a tantalizing possibility that dark matter might be a bridge to other hidden realms, dimensions, or even entire universes. These ideas, while speculative, are rooted in the quest to understand why dark matter is so elusive and how it fits into the broader fabric of reality. Could dark matter be evidence of a multiverse or a shadowy parallel world intertwined with our own? The concept of a multiverse arises naturally in certain theories of physics, particularly those involving quantum mechanics and string theory. In these frameworks, our universe may be just one of many, each with its own set of physical laws and properties. Dark matter, with its mysterious behavior and lack of interaction with light, could be a clue to the existence of these other universes or dimensions. One of the most intriguing ideas is that dark matter might consist of particles that exist in a dark sector, a realm of particles and forces that interact weakly, if at all, with ordinary matter. This dark sector could include not just dark matter, but also dark radiation, dark electromagnetism, and even dark stars and planets. If such a sector exists, it might resemble our own universe in some ways while remaining fundamentally hidden from direct observation. Theoretical physicists have proposed mechanisms by which the dark sector could interact with our universe. For example, dark matter particles might interact with ordinary matter through gravity or weak forces, providing indirect evidence of their existence. Alternatively, certain dark matter candidates, like axions, could oscillate between ordinary and dark matter states, creating subtle effects that could be detectable with advanced experiments. The idea of a dark sector is not just theoretical. It is being actively tested in laboratories and observatories. Experiments like those at the Large Hadron Collider are searching for particles that could act as messengers between our universe and the dark sector. Meanwhile, astrophysical observations are probing the distribution and behavior of dark matter to identify any anomalies that might hint at interactions with hidden dimensions or forces. Another avenue of exploration is the possibility that dark matter could interact with gravity in unconventional ways. If dark matter exists in extra dimensions, as some theories suggest, its gravitational influence could leak into our universe, affecting the motion of galaxies and the behavior of large-scale structures. Observing these effects would provide direct evidence for the existence of higher dimensions and the role of dark matter within them. The connection between dark matter and the multiverse also raises profound questions about the nature of reality. If dark matter is linked to other universes or dimensions, it could offer a glimpse into realms that operate under entirely different physical laws. Such a discovery would challenge our understanding of the cosmos and redefine our place within it. Gravitational waves, ripples in space-time caused by massive cosmic events, might provide another way to probe the connection between dark matter and hidden realms. Certain theories suggest that dark matter halos, or black holes associated with dark matter, could generate unique gravitational wave signals. Detecting these signals could reveal the influence of dark matter beyond our universe. offering a new perspective on its role in the multiverse. Cosmic phenomena like the cosmic microwave background, CMB, and the distribution of galaxy clusters could also hold clues to the existence of hidden realms. Subtle anomalies in these datasets might reflect interactions between our universe and other dimensions, or the effects of dark matter from parallel worlds. By analyzing these phenomena with increasing precision, scientists hope to uncover patterns that point to the existence of a multiverse. The search for a connection between dark matter and hidden realms is not without its challenges. Many of the proposed effects are subtle and difficult to detect, requiring advanced technology and careful analysis. Moreover, the theoretical frameworks that underpin these ideas are complex and often speculative, demanding rigorous testing and refinement. Despite these challenges, the exploration of dark matter's connection to the multiverse represents one of the most exciting frontiers in science. It pushes the boundaries of what we know and invites us to consider possibilities that were once confined to the realm of imagination. By studying the invisible forces that shape our universe, we gain insights into the nature of reality itself. As we continue to probe the mysteries of dark matter, one question remains. Could the substance that governs the universe's structure also be a window into hidden realms? The answers may forever change our understanding of the cosmos, revealing a multiverse of shadows where the boundaries of reality are redefined. The dark matter dilemma. What if we're wrong? For decades, the existence of dark matter has been one of the cornerstones of modern cosmology, supported by evidence from galaxy rotations, gravitational lensing, and the cosmic microwave background. But what if our understanding of the universe is fundamentally flawed? What if dark matter, as we currently conceive it, doesn't exist? Enter the dark matter dilemma, a provocative thought experiment that challenges the foundations of cosmology and opens the door to alternative explanations. The idea that dark matter might not exist is not new. Some physicists have argued that the phenomena attributed to dark matter could instead result from our incomplete understanding of gravity or the structure of space-time. If these alternative explanations are correct, it could mean that our current models are missing a deeper layer of reality. One of the most prominent alternatives to dark matter is modified Newtonian dynamics, MOND. MOND proposes that Newton's laws of motion and gravity break down at very low accelerations, such as those found in the outskirts of galaxies. By modifying these laws, MOND explains the flat rotation curves of galaxies without invoking unseen mass. While MOND has had success on galactic scales, it struggles to account for phenomena like galaxy clusters and the large-scale structure of the universe. Another approach involves modifying Einstein's general relativity, the theory of gravity that underpins modern cosmology. These modified gravity theories, such as F, R, gravity, or Tevis, aim to reproduce the effects attributed to dark matter while remaining consistent with the observed expansion of the universe. Some models introduce additional fields or dimensions to modify the behavior of gravity, creating effects that mimic dark matter's influence. However, these theories face significant challenges, particularly in explaining the separation of visible matter and gravitational mass seen in systems like the Bullet cluster. Quantum mechanics has also inspired alternative explanations. Some researchers propose that the apparent effects of dark matter could result from quantum phenomena on cosmic scales, such as the entanglement of particles or the influence of vacuum energy. These ideas, while speculative, highlight the possibility that the universe operates on principles we do not yet fully understand. If dark matter does not exist, what would that mean for our understanding of the universe? The implications would be profound. The lambda-cold dark matter, lambda CDM, model, which describes the universe's evolution, relies on the existence of dark matter to explain everything from the formation of galaxies to the behavior of galaxy clusters. Without dark matter, this model would need to be replaced with a new framework that accounts for the same observations without invoking unseen mass. The consequences would extend to particle physics as well. Many theories beyond the standard model, such as supersymmetry, predict the existence of dark matter particles. If dark matter is not real, these theories would face significant challenges, and the search for new physics would take an entirely different direction. Testing the dark matter dilemma requires a combination of observational, experimental, and theoretical approaches. One way to resolve the question is to search for deviations from general relativity or Newtonian physics in extreme environments, such as near black holes or in the early universe. Observations of gravitational waves, the cosmic microwave background, and the distribution of galaxies offer opportunities to test these alternative theories. Experiments designed to detect dark matter particles, such as LUX Zeppelin or AMS-02, also play a critical role. A failure to detect dark matter in these experiments over the coming decades could lend support to alternative explanations, though it would not definitively rule out dark matter. Instead, it would challenge scientists to refine their models and explore new possibilities. Another approach is to improve our understanding of the visible matter in the universe. Baryonic effects, such as the influence of gas, stars, and black holes, could account for some of the discrepancies attributed to dark matter. Advanced simulations that include these effects may reveal whether dark matter is truly necessary to explain the observed phenomena. Despite the challenges, the dark matter dilemma is a valuable exercise in scientific exploration. It reminds us that science is not about dogma, but about questioning assumptions, testing hypotheses, and refining our understanding of reality. Whether dark matter exists or not, the search for answers drives innovation and expands the boundaries of knowledge. If dark matter is ultimately disproven, it would mark a paradigm shift in cosmology and physics, comparable to the transition from Newtonian mechanics to Einstein's theory of relativity. It would force us to rethink the universe's structure and the fundamental forces that govern it, opening new avenues of discovery. As we confront the possibility that dark matter might not exist, one question remains. Could the true nature of the cosmos lie beyond our current understanding? The answers, whether they confirm or refute dark matter, will deepen our appreciation for the complexity and mystery of the universe. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.